So welcome everybody. I want to say just a few words about this new day that you will attend today. So you have to know that we have the chance that we are meeting within the framework of 360 Carla. It's a project. We were 13 partners all over Europe, and these partners organized an event. The same kind of event that we organize could be symposium, training, and there are also experiences. We could discuss about that later. And there were four topics that could be addressed to do such event. And we decided at the European Optical Society, because you are here because we organize as EOS this event, we were concerned by manufacturing and industry. So the talk today will speak, but it will be training, but it will show application, of course. Next. Thank you. So Carla program, we have to know it's a second turn. It's a European project. And it offered to participants as round-up cohesive career activities based in the 4 photonics fields. We are concerned by photonics and here by manufacturing and industry. That's why you see that all the panels, all the publicity that we put everywhere are this orange background. Next. So I want to emphasize today, again, and it is important, the organizing team. So you see myself, of course, but David Ferrand from Grenoble University and Nathalie Destouche. We work together during several months closely to make this event a success. And I hope that today you will be happy also. Of course, EOS will not work without Elina Kostinen, the EOS Executive Director, and EOS Communication and Events Assistant Bogie, I will say. Yeah. Without them, nothing would be possible. And we decided to organize this event at NÉEL Institut, and the chief at NÉEL Institut has been Florence Fernandez. And really, we have to thank her about that. And she was not alone. Other administrative from here, NÉEL Institute, help her. And also, today, we have the chance that we have company technical events making this event on-site, but also online. So I thank also people who are joining us online. And this wouldn't be possible without their collaboration with the computer guy from NÉEL Institute. And one of them was Bernard, who is at the back. You will meet him perhaps later. So next, training today, this morning, lectures, this afternoon, experiments. Next. So we don't forget that it was a commitment between EOS, SFP, and SFO, NÉEL Institute, CNRS, and UGA. And it was founded by Photonics 21, who founded this project. And we completed with sponsor graduate school of UGA, Quantalps, that is the LabEx, local LabEx, and the LabEx Manutech Size University of Lyon. This was managed by Nathalie because students from her university joined us yesterday, by bus. Next. So the speakers this morning, first one will be Antoine, then Dorian, then Villasini, and they will introduce themselves more than I will. And this afternoon, for those of you who would like to use the training sessions, if you register, it's perfect if you are here. If you're still wondering if you could join, please ask us, because we could consider that. Benoît Boulanger, David Ferrand, Thierry Chanelière, and myself, we train in our experiment. Next, please don't forget to scan as much as you want this QR code, or go to the website and you will have an overview about the program of today. Thank you.
It works, yes. Thank you, Patricia. So good morning, everyone. I'm Benoît Boulanger, professor here and researcher also here. So I have the pleasure to introduce Antoine Godard. So Antoine is a great guy, president of the Société Française d'Optique, the optical society, French Optical Society. He's also one of the directors of ONERA, the French aerospace agency, and he's also an expert in nonlinear optics. So Antoine has 80 slides for 40 minutes. So yes,
let's start. Yeah.
So 40 minutes, and then we have the question for the end, the 10 last minutes.
Yeah.
So Antoine, please.
So thank you, Benoit. Well, so good morning, everyone. So don't be scared. Maybe I will skip some of my slides, but it's hard to. At the origin, it's a longer course. I try to shorten it for 40 minutes, but it's hard. Yeah. So we skip that. So here's the outline of my talk. So first, I will present some basic principle of nonlinear three-wave mixing in optical media, but the nonlinear response. And then a quick focus on difference frequency generation, and I will discuss a lot of very important aspect for parameter in nonlinear conversion, which is the phase or quasi-phase matching, which is a condition you have to satisfy to have an efficient frequency conversion. And then I will discuss some variation of parametric sources, amplification, generation, oscillation, and some related application. So first, I would like to start with the first big milestones in nonlinear optics. This milestone being the Franken's experiment that has been done in 61 by Peter Franken and collaborators. So they start with a ruby laser that was invented by Mayman very soon before the experiment. They focus this laser in a quartz material, and thanks to the high intensity and high electric field of the that is enabled by the laser, the invention of the laser, you can excite the nonlinear response of the material and thus generate, in addition to the transmission of the laser, classical transmission, you have the generation of a second harmonic wave at half of the wavelength or twice the frequency of the optical frequency. And there is a funny story about this first experiment, because when you look at the paper as it was published, at those times they don't have digital spectrometer and so on, so they use a photographic plate to measure the signal after the prism here. And so here you have the fundamental wavelengths, and here you expect to have something as a second harmonic, and there is nothing here. Actually, there was a tiny spot, and the editor of the journal considered it is a dust, so they remove it from the picture. So the proof of second harmonic generation is not present here. So before artificial intelligence, you already had some fake or fake picture. Just to make sure, I also get the original plates, and the spot was here. So it was really a demonstration of second harmonic generation, but in the original publication, it is unfortunately removed. So now, after this short introduction, so let's go back to I have to discuss a little bit some equation to explain, because it is a tutorial. So the first thing you have to consider is the polarization of the material. So this polarization is the source term in the Maxwell equation. So it will radiate the electric field that from the material, and which is excited by an incoming wave whose electric vector is E. So in classical linear optic, you have only the linear susceptibility that is involved. And so this linear susceptibility is directly related to the refractive index of the material. It is a second order tensor, because you can have ordinary and extraordinary refractive index in some materials. And then, if your electric field is strong enough, you will have nonlinear terms that can be written in this as an expansion, as a Taylor expansion. And this is tensors. So today I won't go to the detail of the tensors, but you have to imagine that it is not, you have big matrices and you have to do matrices product and so on, depending on the orientation of the field and the electric and the crystal axes. And these terms are the nonlinear terms, and this one is the terms that if you excite with one frequency omega, you will have the square of the electric field that will radiate at the second harmonic frequency. So just to have an idea of the relative magnitude of these nonlinear terms, you can rewrite the polarization this way. So these eta coefficients are of the same order of magnitude, and here you have the ratio of the incoming electric field to the intraatomic electric field, whose value is written here, so 10 to the 11th volt per meter. And so as long as you don't are involved in high field physics, as the high field physics, for instance, presented yesterday by Anne Lullier, but in most of the time, this E field is much smaller than the intraatomic field, and so the relative magnitude of each of the terms are decreasing very fast. So in most of the time, you can reduce this expansion to the first nonlinear terms. So in non-centrosymmetric media, Chi2 is, you only have to consider Chi2 in most of the cases. And when you are in a centrosymmetric media, Chi2 vanish. I don't have time to explain because it is a reason of symmetry in the material. And so you have to consider Chi3. But in this tutorial, I will only consider non-centrosymmetric material. So I will only discuss Chi2 quadratic nonlinear optics, which is already largely enough for 40 minutes. And so just to go to continue on this, so let's consider that you shine your nonlinear material with two monochromatic waves, written this very classically. So it's monochromatic, so the temporal variation is exponential. And then if you mix them with Chi2, so you can have the generation of polarizations that will radiate a field that could be at the sum of the two incoming waves. So you can have some frequency generation. You can also have different frequency generation if you consider that actually you have the complex conjugate of its real field. So you have this plus the complex conjugate. So you have also different frequency generation when you combine E1 with the complex conjugate of E2. You can have frequency doubling and many other possibilities. So how then do you calculate how the generation of the new field? So you start with Maxwell equation. So I don't have time to explain how you, and then you get to this propagation equation. So without the nonlinear, if this term is equal to 0, you have the Helmholtz propagation equation, whose solution are the plane waves. And then, in addition to this, you add these nonlinear terms that will excite this E1 field. So you can then introduce envelope functions. So you write E1 as the spatial variation of E1 this way. So you have a slowly varying envelope and a fast carrier with a wave vector K1. And then you calculate this derivative. So I will go very fast. So here you have the dispersion relation because you consider plane wave here. So plane wave are solution of the linear equation. So these terms cancel each other. This term is slowly varying. So at the end, you have this equation that you can and you can take here the wave vector and put it in the other side of the equation, and then you get to this coupled wave equation, which is quite simple. So you have a first order differential equation of E1. So as the source term, you have the product of the two incoming field E3 and E2, and you have this term referred as the phase mismatch, which is very important to consider, because if you want to have an efficient transfer of energy from the generation of E2, you need to have delta K very close to 0. Otherwise, you have here a fast oscillating terms that will result in a very inefficient growth of E1. I will detail later. And of course, you can also mix, in the same time, since E2 is present, you also can mix E2 with E3 to generate wave 2, also by difference frequency generation. And also you can have the sum of omega 1 and omega 2 to generate omega 3. So you have the three possible coupled wave equation, which couple together the three waves. So now let's have a look at a case, which is one of the most simple case. Now we consider that you have two incident waves at frequency omega 2 and omega 3. And these incident waves are very high power, and you assume that you have a low efficiency. So in this way, you can consider that the wave 2 and 3 remain constant during the nonlinear interaction. And so you only have to solve the equation of the generation of the difference frequency wave E1. So you consider that these two terms are constant because when they are mixed with the derivative are equal to 0. And so it's quite simple to solve this equation. So you have, if you consider the intensity, which is typically the square of this field, you can see that you have first parabolic growth, so as a function of the distance, the square of the distance, and also you have this parameter that depends, this sinc function that depends on the phase mismatch, and which gives you the global efficiency. If this sinc, for instance, is equal to 0, you will have no conversion efficiency. So you have to maximize this parameter to have a high conversion efficiency. So if delta K is equal to 0, you will have a parabolic growth, while if delta K is not equal to 0, you can rewrite this way. So the parabolic growth disappears, and you have a sign variation here. So you can see that you start to convert, and after a distance that is referred as coherence length of the material equal to pi divided by delta K, you will have the sign function reach a maximum, and then it will decrease to 0 and again and again. So you have a very inefficient conversion whose maximum value is proportional to 1 divided by square of delta K. So as a nice illustration of that, I have some picture I get from a course tutorial given by Professor Rick Trebino from Georgia Tech. So here's the case of second harmonic generation, but it's similar to different frequency generation. It's the opposite process with degenerate omega 1 is equal to omega 2 in this case. And when you are far from phase matching, you can see the sinusoidal generation of the second harmonic generation, which is not very efficient. And then if you change the orientation of the crystal, I will then explain you how does it work. You can reduce the phase mismatch, so you can get closer to phase matching, and you can see that the coherence length increases, and also the maximum, the intensity of the second harmonic generation is also higher. So it can be seen that the second harmonic beam is more intense when you get closer to the phase matching condition. And also you can understand that you don't need to be at perfect phase matching to have an efficient conversion efficiency. If the length of your crystal is shorter than the coherence length of the second harmonic generation, you will still have a high conversion efficiency. Actually, if you again look at this sinc function, it gives you the acceptance of the second harmonic generation. When you are at perfect phase matching, you have a maximum efficiency, but if you are a little bit away of this perfect phase matching condition, you can still have a high efficiency. You can define a bandwidth, so I don't go too much into the detail. You have several definitions. A usual one is to consider that that the bandwidth of the acceptance bandwidth correspond to a value of delta K where the coherence length is equal to the length of your crystal. And if, of course, if the crystal is twice shorter, you have a broader acceptance, but of course a lower efficiency, since the efficiency is proportional to the square of this L value. So actually, phase matching is very important because if we go back, I mentioned earlier that you have many possibilities of nonlinear frequency generation. You can have second harmonic generation, some frequency generation, different frequency generation, and so on. And so why do you have only one process that is efficient? Usually you only need one. You don't have to have a lot of frequency generated. You want to generate one specific wavelength. And actually, since you have to satisfy this relation, of course, which also is referred as a conservation of energy, meaning if you think about photons, it means that the energy of the two photons must be equal to the energy of the generated photons here. But in the same time, you have to satisfy phase matching, and to satisfy phase matching, you add the refractive indices of the material, and since you have dispersion, usually it's not possible in most of the case to satisfy these two equations for many couples of frequency. So usually only one of the process is at phase matching, while the other one are not phase matched, and so only one is efficient. So you can only consider the one that is phase matched. But up to now, I did not explain you how you achieve this phase matching, because if you look at this material, in conventional material, due to dispersion of the material, the refractive indices usually at omega 3 is always higher than the refractive indices at omega 1 and omega 2 due to dispersion, and so you cannot satisfy both equations at the same time in an isotropic material. So the first approach is to use birefringence to compensate the chromatic dispersion. So you can explain it here in the case of second harmonic generation. So consider that you have a material with an ordinary and an extraordinary index of refraction. So I don't know if you already heard about this kind of material. So you have, depending on the polarization of your wave, you have two different index of refraction. And let's consider that the fundamental wave is along the extraordinary direction, while the second harmonic generation is ordinary. So you have a difference between this ordinary and extraordinary indices, which is referred as the birefringence of your material. And then if you properly select the orientation of your material, you can have the refractive index, the extraordinary refractive index at omega equal to the ordinary refractive index at 2 omega, and this way you have your phase matching condition. So this approach was demonstrated since the 60s. For a long time, it has been the only effective method to carry out nonlinear frequency conversion. So you can here you have an example, for instance, of a tunability depending on the angle of a material. You can select the wavelength that is phase matched. It is work that has been carried out here at Institut NÉEL by the team of Benoît and Patricia. But you have few limitations with this approach, because you can only use birefringent materials, and some very interesting nonlinear materials are not birefringent. You have double refraction, and also, since you have to choose the orientation of your crystal that achieve phase matching, usually it's not the same direction that provide you the highest nonlinear coefficient. So you have to choose an orientation which is not the one you would have you want to use if you want to have the maximum nonlinear efficiency. Another approach, which is now widespread and maybe dominant in many cases, is the use of quasi-phase matching. So the idea is to deal with the phase matching. So you know you are in a material that is where delta K is not equal to 0. So if you don't do anything, as I already discussed, after occurrence length, you will destroy what you generated and so on. But now let's consider that you have a material when you can periodically invert the sign of your nonlinear coefficient. after each coherence length, you invert the sign of your nonlinear coefficient. So you have a kind of nonlinear gratings. And so since you invert the sign here, an inversion of the sign is equivalent to a pi phase shift. So you can reset the phase between your wave and restore a constructive process. And so this way, you can have you can maintain the efficiency towards the wave you want to generate. So this is referred as quasi-phase matching, and you have a generalized phase matching condition where, in addition to the wave vector of 1, 2, and 3, you have an reciprocal lattice vector of the nonlinear grating that add to it, and then you have a generalized phase matching condition that you have to satisfy for an efficient conversion efficiency. So it is at first glance it could look less efficient because you don't have a nice parabola. You have this very funny curves like that. But since you can always solicitate the largest nonlinear coefficient, usually it's still more efficient. And also you can engineer your nonlinear grating, which open the way to many potentialities you cannot have with phase matching, traditional phase matching. So how you achieve quasi-phase matching? The first approach is to use ferroelectric nonlinear materials. The mostly well-known is lithium niobate. So then you add periodic electrode, you apply a high voltage, and this way you can invert the polarization of your material when this voltage is larger than what we call the coercive field of the material. And then, thanks to that, you can have stable periodic polling of your nonlinear coefficient. Another, and so I don't have time to detail this. Another approach is to directly grow orientation pattern materials. That you can do this on semiconductor, which is very interesting also because gallium arsenide, for instance, enables you to go far to the infrared, which is not possible with lithium niobate, which absorbs wavelengths above typically 4 or 5 micrometer. And this is more recent because it was very hard to develop the process to did this direct epitaxial growth of orientation pattern materials, but now it works quite good as well. And then I also tell you before that you have some engineering. So if you have just periodic polling, so it's equivalent to classical or birefringent phase matching. So you will have, at the same time, as explained before, this acceptance of the process provided by a sinc function and with an acceptance bandwidth corresponding to delta k equal to the coherence length of the material, in the material. But since you can engineer the polling, you can have, for instance, chirped polling, which enable you to broaden the bandwidth, which is something that is not achievable in a conventional birefringent material. And you have also many other variations. You can have a parallel grating, you can have fan-out grating, a periodic. You can also do it in a guided wave, nonlinear optics. And also more recently, people managed to have very, very short period in such a way that you can achieve a phase matching also in one of the waves being propagating backward to the two other one, which is a very also interesting device. Maybe I will give some details if I have time about that. So now I try to introduce you the basic, especially the phase matching and quasi-phase matching, which is a very important aspect to have an efficient conversion. And now let's consider another case. So I just recall here the coupled wave equation. So just to remind you, so this equation I rewrite them with normalized parameters, but you have this delta k and the mixing. When you, by difference frequency generation, you mixed what we call A3 is often referred as a pump with the complex conjugate of the other wave and so on. And then you have some frequency generation when you don't have the complex conjugate. So let's consider the case of parametric amplification. So in this case, we consider that we have a strong wave at omega 3, which is often referred as a pump, and then you mixed it with a small incident wave omega 1. And in this case, you consider that the efficiency of the frequency conversion is not very large, so you consider that the pump wave remains constant during the interaction. So in this case, you have to solve this two coupled equation, where the pump intensity is now inside this parametric small signal gain, which is considered constant in this case. And when you solve this equation, it's quite straightforward, especially if you consider that E2 is equal to 0 at the input of the crystal. So you have the amplification of E1, which is referred as parametric amplification, provided by this hyperbolic cosine function. And in the same time of this amplification, you have the generation of wave E2 that it was not present at the entrance of the crystal and is then generated by difference frequency generation. And this is so the generation of this. So the E1 is often referred as a signal and E2 as the idler. So you have a gain in nonlinear crystal, which is given by this. When you are in a high gain, the hyperbolic function simplified to this exponential, which is familiar as the approach where, for instance, in laser oscillator, when we have this exponential growth. But after some propagation, you cannot longer anymore consider that the pumping is constant, because you will deplete the pump to amplify signal and idler. And so you have to solve the equation considering also the depletion of the pump. You have solution. I don't want to detail them because it involves a Jacobi elliptic function, but you have some solution. But you can see that the pump is depleted, and when you have a total depletion of the pump, then you will reconvert the pump and decrease the signal, because signal and idler will then carry out some frequency generation to regenerate the pump, and so on. On top of that, you can also add phase mismatch, which reduces the efficiency of the process. So you need to be at perfect phase matching to have the most efficient parametric amplification. So you have actually two processes already discussed. So you have the sum frequency generation, which can be considered as a nonlinear loss for the wave if you want to amplify wave omega 1. You have the difference frequency generation. So you mixed one photon at omega 3 with one photon at omega 2 here, and so you generate difference frequency generation, and in the same time you amplify the wave at omega 2. So difference frequency generation and parametric amplification are the same process, actually, two sides of the same coins. And you have actually a third process that I did not discuss yet. Let's consider the case where you have only the pump that is incident, and then you can also spontaneously generate two waves by parametric generation, or parametric fluorescence, or spontaneous parametric Dunn conversion. You have this three names for the same process, which is actually intrinsically quantum phenomena. So I don't have time to details because you have to resort to quantum optics if you want to capture all the correlation between the fields. But it is, I just have to mention that it is a workhorse of many quantum optics experiments. For quantum cryptography, quantum information, people use this spontaneous parametric Dunn conversion to generate twin photons that can be exploited for their quantum properties. Yes, this I don't detail. But now let's consider that you shine this kind of crystal in continuous wave regime with 1 watt. So in the case of lithium niobate, and you can, if you shine 1 watt and you calculate the gain, you can see that the parametric gain is quite small. So you won't have a lot of photon generated at the output of the crystal. So if you want to have an efficient conversion efficiency, you have actually to do the same as we do with laser. So you put your nonlinear crystal inside a resonant cavity to provide feedback. And if the loss of your cavity are smaller than the gain of the crystal, you can reach oscillation, and then you have an optical parametric oscillator, which enables you to convert the pump efficiently toward a signal and idler, and also to have a tunability of if you change the temperature of the angle of the crystal, you can select which wavelengths are generated efficiently. So the first OPO was demonstrated soon after the second harmonic generation by John Main and Miller. So you can see a picture of this first OPO. It was actually a monolithic OPO because the dielectric coating were directly put on the crystal. You can see that at those times they were in the lab with ties and shirts, which is maybe not anymore the case. And since you have 3 waves, you are many possibilities of resonator configurations that you don't have with laser, because you can have what we call the singly resonant OPO. So one wave is oscillating in the cavity. You have the pump, and then you have the generation of the idler, and so you have to consider this singly resonant OPO, which is quite simple, but with a rather high oscillation threshold. But since you have 2 waves, because the idler can also be amplified in the crystal, you can have a doubly resonant OPO when you have 2 cavities and so you can have a lower threshold, but it's more complex to implement. And you have also other possibilities that totally non-existing with laser. You can have the cross-resonant or non-resonant OPO with one mirror reflecting the idler, the other reflecting the signal. And since they are non-linearly coupled in the crystal, you can define an oscillation threshold and a steady state solution. The backward OPO, where I already discussed, when you have a distributed feedback inside the crystal, nonlinear distributed feedback that also can reach a steady state and an oscillation. And you can also have a triply resonant approach when you have a 3-wave resonating inside the resonator. This way you can have very low threshold below the milliwatt, but it's quite difficult to stabilize. So just let's move. So how to define the threshold? Very fast. So it's like in a laser. So you start with a field, you amplify it with this hyperbolic cosine. Then you have some loss on the mirror, and the threshold is defined when you are gain equal to loss. So you can thus define an oscillation condition. And also, it is a resonator, so you will have modes, like in a laser. 5 minutes. Okay. So maybe I will need 10 minutes, I think. And you can calculate this threshold still in the case of lithium niobate with the same parameter. And typically, sorry, there is some French here. Threshold, say is threshold. And typically, in this case, for instance, the threshold is around 3.4 watt in this case. So here you have a typical implementation of such a continuous wave OPO currently. So if you already see a titan sapphire laser, it's very similar. So you need a highly focused beam to have a decent gain, stable resonator with high reflection coefficient. So it works quite good. You can see you can reach very high conversion efficiency. In this paper, for instance, they demonstrate close to 100% efficiency in the OPO of pump conversion. But it's still, I will say, it is still devices that are very hard to get out of the lab, this kind of bulky single resonant OPO, because you really have to maintain a very stable alignment, very nice alignment. So that's why currently the work effort, the research effort is focused currently on the development of integrated photonic circuits with on-chip OPO. So you have here quite recent paper. I encourage you to read if you are interested. It is a review paper. You can see that now we are toward very small, tiny OPO chip. So it's very interesting for many applications. But for other applications, you don't want this kind of chip because you want to have power. You have applications where you really need to have power out of the OPO. And in this case, the best is to use the OPO in pulsed regime. So the preferred operation regime in this case is the easier to implement is the nanosecond regime, so because you can use the high peak power of Q-switch laser, which enables you to reach very high gain, and so you can have very compact resonator with only a crystal and 2 mirrors. So you can see here you have a pump pulse. First, your oscillation has to build up from quantum noise, and then you have a quite efficient conversion of the. In green, you have the signal, and in red, you have the idler power. Now, what kind of application you have with this nanosecond OPO? You have a first one of the application is to protect aircraft from missile. Because missiles, they target the infrared signature of aircraft. They look at the high temperature part of the aircraft. And so using an OPO, you can shine the missile and jam it. And another, maybe more, I would say, peaceful application that we are working a lot on at Onera currently is the gas detection with LiDAR. So you use the tunability of your parametric source to be able to switch between two wavelengths, referred as lambda off and lambda on. Lambda on is absorbed by a gas you want to measure. Lambda off is out of absorption. And then you switch the two. You launch this laser in the atmosphere. And then you have a backscattered signal. And if you compare the signal you get at lambda on and lambda off wavelengths, you can recover the absorption and the concentration of the gas inside. Can be greenhouse gases, industrial gases, and you have many applications on that. I will skip this because I don't have time, I think, to explain I already tried to mention that the threshold in pulse regime actually is higher than in continuous wave regime because you have to construct from quantum noise the oscillation. So even if you are above the continuous wave threshold, you need to pump it high enough to get some signal before the end of the pump pulse. So usually your threshold in pulse regime is 3 or 4 times above the threshold in continuous wave regime. Another very important thing I would like to discuss very quickly is the spectrum, because if you want to do gas detection, you need to have a narrow line width that you want to switch between lambda on and lambda off. But if you don't do anything, you just put your crystal in a cavity. Many modes, since you have a high gain, many modes can oscillate, and you have usually a multi-mode emission. Also, from pulse to pulse, the spectrum can vary a lot because it starts from quantum noise. So you have to develop strategies to get narrow line width. Actually, you have 3 main strategies. The first is injection seeding. So you start with a very narrow line width laser, and you inject it in your OPO cavity in such a way that instead of growing from quantum noise, it grows from this narrow line width seed, and so you have narrow line width emission. You can add also diffraction grating or prism inside your cavity to have wavelength selective loss. And a third approach is to use the Vernier spectral filtering. Maybe I will detail very fast this. So injection seeding is quite straightforward. So without seeding, you have this multimode emission, and you have some seed here. So you start at the seed frequency, and the other modes don't have the time to construct before the pump is depleted. And this way, you have this narrow line width emission. But tunability is not straightforward because I already consumed my 5 minutes more, or it's no? Yes? It's 45 already?
3 minutes more.
3 minutes more. So okay. So I need And so you need a tunable pump. So then, unfortunately, I won't have time to detail how you can get single frequency emission in doubly resonant OPO. I just want to show you some picture of parametric sources that we use for LiDAR. So here it's in a truck. And to measure water vapor and isotope of water vapor from an aircraft or from a truck, which is important for climate scientists. And you have other technological maturity for onboard system, and here you have systems that we put on an airplane to do this measurement. This I will skip it. I just want to mention maybe 2 minutes more to discuss the short pulse regime. So in short pulse regime, maybe you will have the opportunity to visit some experiment later. You have actually a very, very high gain, so you don't need a cavity anymore. So you can start with a femtosecond laser, and then you directly shine the laser on an NMR crystal, and you have an efficient conversion efficiency. In many cases, one part of your laser is used to generate a supercontinuum, for instance, in another material, and you can use it to seed this optical parametric amplifier. You have also OPCPA that were maybe mentioned yesterday by Anne Lullier. It's an approach to reach very high intensity. You stretch, your pulse, you amplify it, and then you compress it. It's the same as in short pulse laser. This one, my last slide. I just want to mention how you can also have an oscillator with very short pulses. So you can use synchronous pumping. So in this case, you pump your OPO with a mod-lock laser. So a mod-lock laser delivers trains of pulses. And if you have an OPO where the round-trip time inside the OPO is equal to the round-trip time in your pump laser, you can synchronously pump your OPO, and so you can have an efficient conversion efficiency if you have the same round-trip time in your OPO and in your laser. And thanks to this approach, you can generate, for instance, a very broad spectral emission also for spectroscopic application. So sorry for this presentation was too long, but I finished. I let you read the conclusion.
Thank you very much, Antoine.
Oh, I start at 4, at 15.
So it's a very good introduction for the training of this afternoon.
Yeah.
And we have time for questions.
Yes?
Thank you for the presentation. There's something that I maybe missed is that when you do quasi-phase matching, what prevents you to do a material? Yes, thank you. So my question was, when you do a quasi-phase matching, what prevents you to have a very long material? Is it absorption? Is it you need to be very precise when you engineer the length?
The length of the material.
The total length, yeah.
I think the longest in bulk crystals, the longest is technological limitation. Actually, it's not the absorption. It's the longest you can buy is something like 6 centimeter length. It is because they do it on a wafer of lithium niobate, and I think its limitation is only due to the technological process, the size of the wafer, and it's not the absorption, because it could be 60 centimeter for in bulk optics. It will be hard to have a longer crystal because you use Gaussian beam, and the aperture of one limitation I did not mention in periodic polling is that it's like the thickness of the material is usually limited to 2 or 3 millimeters. It's very hard to make thicker material. So if you have a very, very long material, then it will be hard to handle a beam inside due to diffraction of the beam inside the crystal.
Okay, thank you.
Yes.
Just to understand, like when you're talking about like OPO, like resonators, like
Yeah.
it's kind of similar to a laser, but like a laser, it's like a single, it's the same, how to say? In an OPO, you are increasing or decreasing the frequency of the.
You are in the kind of OPO, you are only can do done conversion, so you are increasing the wavelength or decreasing the frequency.
Okay.
It's always at smaller frequency or longer wavelengths, your generation.
Okay.
To have gain, you have to go downward. If you do some frequency generation, you can, or second harmonic generation, you can generate higher frequency, but in this case, it's a no gain process. It's only, you consume two of the two waves you mix. Mm-hmm.
I have one, Benoit. Yes, could you show the backward OPO, because it is really a new thing, very interesting.
So it's a very interesting, yeah. So I just go back. So you have some extra time for that. So what are the motivation? Actually, I skipped that, but I already I discussed strategies to get narrow line width, but the strategy, all of the strategy involve quite complex system with mirrors and so on. So, but in the world of laser, you have the DFB laser, which is now widespread. In the DFB laser, you have a grating modulation of the refractive index of the materials, which provide a feedback inside the laser and enable to have naturally a single frequency emission. So the idea is to have an analog of this DFB laser, a nonlinear analog, and this analog is the distributed the backward wave OPO, where you have, in this case, a nonlinear feedback, but it's distributed in the crystal. So this approach actually was, as many approaches in nonlinear optics, when you find that you discover something, you have to go back to the 60s paper, and everything was already discovered by or proposed by researchers. So in this case, it was Stephen Harris from Stanford University that proposed this backward wave OPO. But technologically, it's very hard to get the fast matching condition. So actually, I think it is only possible, only demonstrated in using quasi-fast matching. But you need, here you can see that the nonlinear grating vector is comparable to the pump wave vector. So you have to have a very short polling period of typically half a micrometer. So it's technologically, it's very hard to manage for technological issues to do that. So it was the first experimental demonstration was carried out 40 years after the idea by colleagues in KTH in Sweden, by Carlotta Canalias and Valdas Pasiskevicius. And this backward OPO is very interesting because you can reach oscillation without mirror. So it's when you do it in the lab. Maybe I have a picture of backward wave OPO here. So the green here is parasitic second harmonic generation, but what you generate, you shine it with a 1 micrometer laser and you generate infrared. But it's just put your crystal here in an oven because you have to stabilize the temperature, and you shine laser inside and it oscillates. You don't have to align any mirror and so on. So it's like second harmonic generation in terms of optical alignment. And it is naturally narrow line width. And very funny thing also, I don't have time to detail why, but here we in this experiment we have a pump where we can tune the wavelength of the pump. So in this graph you have the frequency of the pump as a function of time. So it's a pump that is seeded by a tunable laser, so we play with. And you can see here the frequency of the forward wave and the backward wave, and you can see that the backward wave remains stable and constant, while the forward follow exactly what we do with the pump laser. And for LiDAR application, it's very interesting because if you have a tunable pump, you can switch from lambda on to lambda off with a proper wavelength change. And then using the backward wave OPO, you transfer this tunability to the infrared at the proper wavelength where the gas absorbs your. So it's a way to translate the wavelengths to the infrared with maintaining all the properties of your pump laser without mirror.
But we have no, it's quite impossible to have angular tuning.
No, but it's, yeah, of course, because it's a distributed feedback. So tunability is mostly with temperature. You can tune it by temperature tuning. You can use a little bit angle, but you have to stay inside the acceptance of the crystal. You will need very big crystal if you want to do some angle tunings. But it's possible to do some angle tunings if it's inside the acceptance of the crystal. Yeah. And the most convenient is pump tuning, actually, if you want. Or to have two crystals. What we want to do in LiDAR also is to have two backward wave crystal, and we switch the pump from one to the other crystal mechanically. Oh, yeah.
Good. So, a last question? No. So we can thank again Antoine.
Thank you.
And switch to the second talk of the morning. So Thierry is the chairman.
So I take the responsibility of the introduction. So I'm Thierry Chenelière. I'm a researcher at the Institut NÉEL. And I will be also animating the training this afternoon for one of the sessions. So we're all set. So it's really a pleasure, a personal pleasure, I would say, to welcome Dorian Bouchet. So Dorian is a researcher at the LIFI in Grenoble. So that's on campus. For those who have been on campus yesterday for the Anne Lillier seminar, that's there. So Dorian is there. So at the LIFI. So you did the PhD, as far as I remember, at the Institut Langevin. So the Institut Langevin, it's in Paris. It's a well-known institute to study, I would say, wave propagation in complex media. When I say wave, that can be optics, that can be acoustics. In your case, it was already optics. When I say complex media, that can be disordered media, complex nanostructure, for example, and in your case, it was plasmonics. Right. So then he joined back a few years ago the LIFI as a CNRS researcher. And I would say for the student in the audience, he's a good example of a young, talented researcher. So you will talk about your current work at LIFI, connected, complex media, and propagation. So the floor is yours. You have, let's say, 50 minutes, and we take 10 minutes for the question.
Thank you very much for the introduction, and thank you for the invitation. Today, I'm going to talk about wavefront shaping in complex scattering media, from light focusing to information extraction. Light focusing is what has been done in the field for the last 20 years, and information extraction is a bit oriented towards my current research line. So to start with, I like to introduce with different perturbation regime, which are going to be used to define what is strongly scattering. And the weakest scattering regime in which we can think is the perturbation of the index of refraction. So here you see that because of hot air, the index of refraction is a bit perturbed, and we can see that this generates phase aberration. We consider that the wave is not really perturbed, but only it acquires a phase delay due to this perturbation of the index of refraction. And then when we go to a stronger perturbation regime, where the index of refraction is very strongly perturbed, we go into the regime of light scattering. And in this picture, we can see the three different regimes. So here it's not perturbed at all. It's ballistic regime. In the middle, we have a single scattering regime, which means that on average, we have only one scattering event from the light source to our eye. And then on top, we cannot see anything at the top of the Eiffel Tower. We are in the multiple scattering regime, in which we have several scattering events during the propagation of the light. You can think about this point model of scattering on this continuous index of refraction perturbation regime as being the same if the index of refraction is strongly perturbed. And this is very interesting to study because it has several applications in astronomy and in biomedical imaging. So you don't do multiple scattering in astronomy because when the sky is cloudy, you don't do astronomy. But even if it's clear, you have perturbation in the atmosphere, which create phase aberrations that you need to correct if you want to do astronomy correctly. And in biomedical imaging, biological tissues, they are very strong scatterer for light. This is why you cannot see through your hand. And if you want to do biomedical optics, you need to handle multiple scattering to be able to see what's happening inside these tissues. So this is how my presentation is going to be structured. First, I'm going to talk about this weak phase aberration and about the application in astronomy. Then I'm going to talk about the multiple scattering regime and how to handle it in order to focus inside strongly scattering medium. And then at third, we will try to understand, instead of focusing, if we can try to extract information from the objects that we are interested in inside the materials. So starting with phase aberrations. As I said, in astronomy, it's necessary to correct for the perturbation of the atmosphere. And if you don't do it, this is what you obtain. So here, it's a double star. So you cannot see two stars. And here it's Neptune, so you can see Neptune, but you cannot really see anything happening inside. So we want to correct for the aberration. And this is a typical setup that we have. So we have the science target, so Neptune or the double star. The light is going through atmospheric turbulences, which distort the wave. And then you collect it with the camera. And what you want is use a deformable mirror in order to correct for the phase aberration in order to get a clear image on this side. So what is a deformable mirror? Typically, you can control between 50 and 1,000 modes to correct the phase aberration. And these are the example of big mirrors from the Very Large Telescope in Chile. So this is the front of the mirror. It looks like a mirror, but if you go to the back of the mirror, you can see a lot of actuators that are independently controlled and moved in order to locally change the path difference and therefore to correct for the phase. So these are the big mirrors of the VLT. Okay, now we have explained the deformable mirror. The question is, what phase do we need to apply to this mirror to correct for the phase aberration? Because we don't know what's happening in the turbulences, and it's changing all the time. So the idea here is to use what is called a guide star. So it's a known point-like source that is either in the sky or in the upper atmosphere that we know is a point, and this knowledge can be used to correct for aberration. To be a bit more precise about guide star, so yes, this guide star, it must see the same aberration of as the science target. If the guide star is too large, too far away, it sees different aberrations, so you cannot use this knowledge to correct. So you have two types of guide star, the natural ones. So here it was our double star, and fortunately, you have a single star that we know is single, very close to it. So here we are happy, we have a single star close to our science target, so this will be our guide star. But many times you don't have this guide star, you don't have luck and there's nothing near the thing that is of interest to you. So the idea is to shine a laser, to shoot a very strong laser in the upper atmosphere to excite the sodium atoms that are in the upper layer of the atmosphere, and then from the signal detected from this atom, you can consider that as a point-like source, which can be used as a guide star. So this is a very expensive way to have a guide star, but all the big telescopes, they have a lot of lasers to act as guide stars. Now we have our guide star. We collect the signal from the guide star, and we need to send it to a wavefront sensor in order to look at which phase aberration this guide star has experienced. So typically, a wavefront sensor is a Shark-Atman. The idea behind it is you have an array of lenses. So if you send a plane wavefront on it, you can see that here locally the wave is plane on straight, and it will focus at these different points. So you have a regular grid array. But now, if the wave is distorted, the phase is still plane here, but it's tilted. And since it's tilted, it will shift the position of the focus in the focal plane, and you will end up with an image like that in your detector. And you can use this position in order to recover the tilt of your and the aberration of your wavefront. So now we have everything. We know what turbulences the guide star has experienced, and we assume that the science target has seen the same turbulences. So we can use a control loop to apply the correct deformation to the mirror in order to compensate for the phase aberration and recover the clear images. And this is what it looks like. So here it's in the Observatoire de Haute-Provence. It was, I think, the first demonstration of adaptive optics in astronomy. So now you can see the two stars. And this one I like very much. It's Neptune. So here you see a very nice image of Neptune taken by the Very Large Telescope. This was an introduction in the regime of weak phase aberration, and it was also an aspiration for all the researchers that have worked on the strongly scattering materials that I'm going to talk about. I'm going to first describe what is multiple scattering of light and how we describe it. So as I said, it's a challenge for biomedical imaging, and you have different regimes in light scattering. So at first, the light is not scattered. Then light is going to be scattered by your tissue, by the atoms, the molecules in your tissues. But the direction will be mostly conserved, because in tissue, light experiences mostly forward scattering. You have less back scattering than forward scattering. So you still keep the direction, but at some point, the direction also is lost. So then the direction is totally randomized. And this is typically the length scale, as that we say, that imaging becomes impossible. And to give you an order of magnitude of the scales involved, this, when you start to have scattering, is about 0.1 millimeter, and this, when you lose direction, is about 1 millimeter. So you say, after 1 millimeter of tissue, I don't see anything. And what's happening when you send a coherent laser light through more than 1 millimeter tissue? Well, this is what you obtain. So it's called a speckle pattern. You see a lot of bright spots and dark spots. And the typical size of the spots is lambda over 2. So in optics, it's, let's say, 500 nanometers over 2. So you have a lot of different spots. So this is what is written here. You have a huge number of modes. To give you an idea, it's 20 million for 1 square millimeter. So it means that you really have a lot of spots, which is also equivalent to have a lot of degrees of freedom that you can play with in what will follow. So now I'm going to talk about the framework and the theoretical way I'm going to describe the field, which will look simple, but it's also a bit unconventional, so this is why I'm taking time to do it. So this is not unconventional, this is very conventional. It's just I'm working with a complex field because I'm looking at only one frequency. And of course, I consider that is a vector because you have a 3 polarization component. In the typical experiment, you send your speckle through a polarizer and you image it onto a camera, and this is what you look like for a given polarization. And if you rotate the polarizer, you have a different speckle for the other polarization because the 2 polarizations are independent. You don't assume the third one because we typically think about it as being in the far field. So you have a transverse wave in the far field, so you don't have the Z component of the polarization. But as you see here, I measure only intensity with the camera, and it's an important point. I'm always talking about the field, but we are measuring only intensity. And it's very different. The field is a complex number, and if you want to recover the field, you need to do interferometry. So you need to send a known reference beam that you combine with your signal beam, and by doing some signal processing, you can recover also the phase of the field, and with this intensity and phase, you have characterized the field. Okay, so this is okay, and now I have introduced you the field as a continuous variable of the position, but in fact you know that your signal is band limited. Because as I said, the speckled grain cannot be smaller than lambda over 2 due to diffraction. So in fact, I don't need a continuous description of the field. I can only sample the field, and it will be sufficient to describe the full information in my speckle. So because of that, I'm forgetting this continuous description, and I'm going to introduce a new vector, which is composed on all the fields at the position of interest. So now this is a vector also, but the components are not the polarization, but they are the position at which the field is interesting to me. And I'm going to typically write it in this way. So if you want to consider both polarization, you can. This is what I've written here, EX and EY. In most experiments, we consider only a single polarization because it's simpler. And then the component is only the position at which I look at the field. Okay, so now let's have a look at what's happening at the input and at the output of a strongly scattering material. So if I send a field at the input here, at the output, I will get a given signal if I put my detector at this position. And the signal will be the result of a lot of scattering inside the material. So this image, I don't like it so much because in practice what's happening is a lot of interferences between the different parts of the field. But you can think about it just as a matter of convenience here. This represents a lot of interferences due to the scattering by a lot of particles in the material. And then if you have another point particle at this position, another point laser source at this position, you see that it experiences a different pathway of scattering, and it can contribute either constructively or destructively to the field measured at this position. So if it's constructive, it will give you a bright speckle spot, and if it's destructive, it will give you a dark speckle spot. And in general, this is how we describe what's happening at this position. The field is the sum of the input field times the scattering coefficient that describe these scattering sequences. This is a complex number also, plus the field at the second position times what's happening in the material at these scattering sequences, and so on. So you see, it's just a linear input-output relation. It's very easy, but in practice, what's not easy is that you have a lot of modes. So you have a lot of terms in this sum that you can play with. And we typically don't write it in this way, but we write it as a matrix relation because it's more easy. So this is the matrix relation. The field at the output is the scattering matrix multiplied by the field at the input. And if you write it component by component, this is the output field, this is the scattering matrix, and this is the input field. So exactly the same relation that I've written before. But now what's nice is that we can think about this you can control, because it's at the input. And this, if you can know this coefficient, you can describe all what's happening in your material in order to predict what's at the output. So we want to access these coefficients that are describing the light propagation inside your material. And in fact, you can measure that. The idea is to send a known input field at the input, let's say a point here at the input. And if you do this matrix multiplication, you see that the output field is simply the first column of the scattering matrix. So this is in experiments how we do measure the scattering matrix. We do it column by column. So we switch then the position of the point. So you get the second component here. This gives you the second column of the matrix, and so on, the third column. So you construct the matrix column by column. And at the end, you have the full matrix. And you can use this matrix to predict what's happening at the output when you control what's happening at the input. And even more than predict, you can optimize, let's say, to try to focus at the output, so get a lot of light at the output by playing with the coefficient at the input. This is a theoretical description of what I'm now going to describe in experiments, wavefront shaping to focus light. So as I said, we need a way to tune the incident wave in spatial degrees of freedom. We want to shape the incident field in space, and you have several ways to do it. Traditionally, it has been done with spatial light modulator. So it's an array of pixels. You have millions of pixels. On each pixels, you have a liquid crystal inside it that you can orientate. And depending on the orientation of the crystal, the phase experienced by the wave will be different. So this is a way to control the phase of a device pixel by pixel. Another way to do it, which is more used now in experiments, is to use digital micromirror devices, which are also the same kind of device that you have in the retroprojectors. It's a bunch of mirrors, very small mirrors, on the order of 10 micrometers, and you have millions of them that you can control individually. So you can either put on or off. If you flip the mirror, the light is deflected elsewhere and you don't consider it. And if it's on, it goes into your path. So it's a binary kind of modulation. But if you do some optics, you can transform this binary modulation into a full amplitude and phase modulation at the cost of you lose some spatial degrees of freedom. So let's say you have millions of pixels of your DMD. You can control even more than 1,000 incident mode, but then in amplitude and phase. Now we are able to shape the incident wave. So we can explain the first experiment of light focusing through a strongly scattering material. This is a situation that I've described before. If you send an incident plane wave onto a complex material, you end up with a speckle pattern. But if you shape the incident wave with a spatial light modulator, in order to pre-compensate the disorder that has been induced by these particles, you are able to focus anywhere, given that you know the scattering matrix coefficients that characterize the medium. In this first experiment, they use a liquid crystal spatial light modulator, which is working well, but which is a bit slow as compared to digital micromirror devices. And as a strongly scattering sample, they used a layer of white paint, let's say. In practice, it was a layer of titanium dioxide, which has the advantage of being strongly scattering and weakly absorptive. But in fact, even if you have absorption, it's not a conceptual problem. It's just that you lose light, so it's more difficult to perform the experiments. And this is what they obtained. So this is a speckle at the input here, and at the bottom, you can see a very nice sharp focus, demonstrating that they were able to focus through a scattering material. What's nice about this story is that you see the speckle doesn't really look like what I've shown you before. It's because it's in log scale. They choose to display these results in log scale instead of linear scale. And the reason why it was before, at the review, it was in linear scale, and the referee thinks it was a simulation because the results were too perfect. So they say, okay, if it's too perfect, I'm going to show them in log scale to be able to show some noise. But it was one of the rare instances where the two good results were playing in their favor. So it's to show you that this effect is actually very strong. You see that it's 1,000 times enhancement as compared to the background. So we are not looking about small effects. And in this demonstration, what they showed is that it's possible to focus through titanium dioxide, but also through a very large set of material, like teeth, scotch tape, eggs, and even tissues. The problem with tissues, it's also moving. All this material, if they are static, everything is happening correctly. But if the medium starts moving, it creates a problem because you want to learn the coefficient and then to be stable, because if the medium is moving, then what you've learned becomes obsolete. And in tissues, the decorrelation time scale is typically in between the millisecond and the second time scale. which means that you can focus if you are faster than the millisecond. Now I'm going to describe the way that they did the optimization. Right now, I didn't mention it very well. I was just saying that if you know the scattering matrix coefficient, you can do it. In practice, they did not know the scattering matrix coefficient, but they did what is called a blind optimization. So they were able to measure the output field with the camera. And in fact, they were measuring only the intensity of the field, so the square num of it. And you can describe it, as I said earlier, as a product of the scattering matrix coefficient and the input field. And if you send just a plane wave, the input field is unshaped, so this is just described by this letter A. And looking in the phasor space, so each arrow represents a contribution of the complex field, you see it looks like a random walk in phasor space, and at the end, the intensity resulting is not that large. And after optimization, what they did is you get the same scattering matrix coefficient, but you tune this incident field in order to compensate for the phase acquired by the wave. So you see this exponential will compensate with this one, and you just have the sum of the absolute value of the scattering matrix coefficient. And what they did in practice is that it was a blind optimization. So they were testing different phases at this location. And if this results in destructive interferences, they were seeing a dark spot in the camera. So they were saying, OK, it's not the good phase. And at some point, they were seeing a brighter spot. And they say, OK, I'm keeping this brighter spot, and I'm going to play with the next mode. So adding some input modes on and on, this results in a very large intensity at the focal plane at the output. So this is the way that they did the optimization. And in fact, they showed through a scattering material, but it's also possible to focus inside a scattering medium. The problem is that you're not able to put a camera inside your strongly scattering medium, so you don't have a way to measure directly the intensity that you want to optimize. But what you can do is use a guide star, as in astronomy. For instance, if you put a fluorescent emitter inside your material, and you use a photodetector in order to look at the light emitted by this emitter, you can arrange a feedback loop in order to maximize the intensity that is detected from the photodetector when you play with your spatial light modulator, so that you can find the good phase of the spatial light modulator in order to maximize the emitted fluorescence that has been detected by the photodetector, and therefore focus at this position. And another guide star that is used by the community is a photoacoustic signal. So let's say you can you take an absorber, an optical absorber, such as a red blood cell, for instance. They absorb light quite efficiently. If you send that sufficiently strong, because of thermal expansion, they will start to oscillate spatially, mechanically, and then to generate acoustic waves. And you can measure these waves and also use that as a feedback in order to focus through scattering materials. Because the more photoacoustic signal you get, it means that the stronger the focus has been on your absorber. And at last, it's also possible to focus using the scattering matrix. So this has been done also. And it's even better than that, because with the scattering matrix, you're not only able to focus, but you can generate any field that you like. Because let's say you control the incident field and you know the scattering matrix, you can just invert this relation. And if you want this output field, you apply the inverse of the scattering matrix, and you know what input field you need to apply in order to get the output field that you like. So this is one of the first experimental demonstrations where they show that they can generate a figure composed of 3 point-like spots due to scattering matrix inversion. Well, now I've been talking about focusing through a scattering material. I'm going to change a bit the idea. We are going to be still inside or through a scattering material, but now the game will be different. It will be to try to extract as much information as we can about a parameter of interest to us. So this is what I just said. Instead of maximizing the energy, so to focus light at a point, can we maximize the information content carried by this wave? And to simplify the problem, we'll consider by what is of interest to us is described as the scalar number theta, which could be, for instance, the position of a target located through a scattering material. So now this is the game that we're going to play. We are going to try to find the incident input field that gives you an output field that is as sensitive as possible to the position of the target, which is located through the scattering material. And why is it interesting? Is that because at the end, if we have an output field that is very sensitive to small fluctuations of theta, it will allow us to precisely estimate the value of the parameter from the noisy measurement that we have at the output. And this has many applications. So this is called parameter estimation. And this has many applications, notably in clear material. So in gravitational wave interferometer, they use this formalism in order to enhance the sensitivity of their instrument to the path difference of the two arms in order to be very sensitive to gravitational wave detection. And here they use coherent light or even squeezed light. And here it's also in clear materials. It's when you want to cool a particle, a levitating particle, down to the ground state. So if you don't want at all to vibrate, then you need to be able to be very precise about the location of the particle, because as soon as you need to be able to estimate its position very precisely, because otherwise, well, it's going to move. So these are examples in free space. It's also very interesting to do it for application in complex scattering material. So here it's a lithography machine by the company ASML, which builds semiconductor chips. And for semiconductor chips, you need to realize that the scale at which it's engraved, it's on the order of 10 nanometers right now. And you have a lot of them. So you have a very large density of semiconductors that are very small. And the problem that they encounter right now, it's not about building the device, it's about controlling their quality. And when you want to control if they have some defects, you need to send light that is quite energetic at this scale, like 10 nanometers, it's in the X-ray, in the extreme UV regime, and it tends to destroy the structure that you just built, which is unfortunate. So for them, it's very important to be able to guide light and to guide only a few photons with a small energy toward the defects to be able to sense if the structures have defects or not. And another application in biology, when you have a cell which secretes protein, you may want to localize the cells on the proteins. For instance, if you want to do super resolution techniques. But everything will scatter light at the border. The cell will scatter light and so on. So you want to precisely estimate some position of cell inside a complex scattering environment. This is for the motivations. Now I'm going to look at the theoretical description. Our aim is to measure noisy data that depends on the parameter. And this noise, we describe it by a random variable x, which is a random vector, which is composed of several random variables. So this is twice that I'm mentioning noise. Actually, noise is not just something in the experiment that you can remove. You can remove some parts of the noise, but at some point, noise is fundamental. It's a property of nature, of quantum physics. You cannot be lower than shot noise, because you see the grains, the photon grains. So in fact, noise is very important in estimation theory. If you don't have noise, you have infinite estimation. So this is not anecdotic that I'm saying noise. It's because we need noise in order to correctly describe what's happening when you try to estimate the value of a parameter. So what I've shown you before is speckles without noise. So I called it the output field. Now I'm adding some noise. So here I'm adding some shot noise, some Poisson noise, which are the measured data x, which is now a random variable because of the noise. And the statistics of the noise is important. And if we consider that you don't have readout noise in your camera and the medium is static and everything is perfect, you end up with a shot noise. On the shot noise, you can show that if you look at the field, and not the intensity, but the field itself, is described as a complex Gaussian variable with a variance of 1/4. Now the question is, how does this random variable depend on the unknown observable theta? Because this is theta that you want to estimate from the data x. Theoretically, we describe it through the likelihood function, which is the probability density function followed by the measured data and parameterized by the value of the parameter theta. And if I want to calculate the likelihood function in my example, I say that the joint density probability function followed by my data is a product over all the pixels, because I have several camera pixels that are measured independently some signal. It's the sum over the marginal density probabilities. And when I'm saying that, I'm saying essentially that the noise is independent between two pixels, which is correct if you look at shot noise. Then I express the marginal densities with the density distribution that I explained earlier, the Gaussian one, which is due to shot noise. And you see that it's parameterized by a variance and by an expected value. The expected value being the output field, and the variance being 1/4, as I said. And then the last step is to say that the output field, so the expected value of this distribution at a given pixel, is obtained from the scattering matrix by simply an input-output relation. So this is the full model, and essentially you see that the parameter dependence is embedded into the scattering matrix that I used to describe my material. Now that we have the likelihood function, let's go back to our original problem, which is to estimate theta from x. To do that, I want to construct a function of my data that will give me the estimated value of theta. So this is my notation. This is an estimator, this function, and hat theta is the estimated value of theta from the data x that I just measured. And there are a lot of different estimators. You can think about building neural networks if you want to build this estimator. The one that is most used in estimation theory is called the maximum likelihood estimator, and it's simply to take the maximum of the logarithm of the likelihood function. So you have the likelihood function here as a function of theta. You take the value of theta that maximizes this likelihood function, which is equivalent to say that I'm taking the value of theta that is the more likely to explain the data that I've just observed. So regardless of the estimators that we take, all estimators are characterized by the bias and the variance. What you want is to have no bias on the low variance. If you have a high variance, it means that, and no bias, it means that on average, you end up with the correct value of your parameter, but you have a large spread around this value. And if you have a low variance but a large bias, it means that you are quite a small spread, but around a wrong value of your parameter. And what you want is, of course, to have both no bias and low variance. And the question that we can now think about is, can I get a variance as low as possible? Because if I get a zero variance, I get infinitely precise estimates. But of course, it's not possible because I have noise. So if x is a random variable, theta of x will also be a random variable. So I will have some variance of my data that will be transferred to the estimated value of the parameters. And the smallest achievable variance is given by what is called the Cramer-Rao inequality, which tells that regardless of the estimator that you use, you will always have a variance that is larger or equal than the inverse of the Fisher information. So we can interpret this quantity, the Fisher information, as the useful information embedded in the measured data about the observable parameter theta. Because if you have a lot of information, the variance can be very small. I'm going to show you the expression of the Fisher information for your curiosity. You have an expected value over the noise fluctuation, and then it involves the square of the derivative of the log likelihood function as respect to theta. So you can say, okay, fair. You can also try to interpret this formula. So to give you a taste of interpretation, you have a derivative with respect to theta, because if this derivative is equal to 0, it means that your measurement does not depend at all of your parameter, so you have no chance of recovering the value of your parameter from your data, because it's completely independent. And why a logarithm? The logarithm is in fact a convenient property for us, because if you have independent events that are described by probability density function that can be described as a product, then it means that the Fisher information is additive, which means that you can simply sum the information that you have from different independent measurements. So this is a property that is needed. This is just an interpretation. In fact, the way that you derive this is from Cauchy-Schwarz. So you have a mathematical demonstration that you can apply, but you can interpret the logarithm and the derivative with these tools. And just to finish on the theory, since we calculated the likelihood function before, then I'm just plugging the likelihood function P that we calculated before into this expression, and we end up with this very nice expression, where you see that this is an Hermitian operator, which involves the derivative of the scattering matrix with respect to the parameter, and this gives you a quadratic form that gives you a real number that is the Fisher information. So now you have a connection between the Fisher information and the input field, so you can play with the input field in order to increase and maximize this number, and therefore to maximize the precision that you will be able to do to estimate theta in the experiment. Which goes to my last part, which is now going to the results that you can obtain in experiments using this formalism. So here I'm starting with describing it in simulation. This is 2D numerical simulation with the coupled dipole method. So in 2D, you can imagine that it's infinite cylinders, each one being a point particle. And you send an input wave from the left. You measure the output field in reflection from the left, and you want to be precisely estimating the position of a target, which is located at the other side of the material. Before maximization, this is what you obtain. So you send a plane wave, and you have a reflected wave that interferes with the original wave. So this gives you this speckle pattern. And you see that you have almost no light that is coming through the material. And after maximization, you end up by generating a pattern that is much more intense at the location of the target, and that will give you a lot of information in reflection about the position of the target. So remember that we are only interested in what's happening here. In fact, here it's even inside the material, so we don't even look at it in principle. But what we want is a reflected field that varies a lot when you change a bit the position of theta. So before optimization, this is what you see at the camera. So here it's a 1D camera because it was 2D simulation. So this is why you don't see an image, but just a line. And you see that if you change a bit the position of theta, it's between the blue and the red curve, it changes very slightly the position of the curve, but it's within the error bars that denote the noise. So, which means that in practice, you will not be able to distinguish the two. And after optimization of the Fisher information, you see that the noise hasn't changed, but the way the field depends on theta is now much stronger, which means that you will be able to separate the two curves much more easily and then to recover the correct value of your parameter. So this is the experimental setup that we've used to demonstrate this idea. At the input, we have a spatial light modulator that we use to generate a shaped input field. We have a scattering layer, which is here a ground glass diffuser, so which was a glass that we depolished in order to make it not transparent. And we measure the output field with a camera. And as you remember, we don't want to measure just the intensity, but we want to measure the field, so we need a reference wave in order to recover the complex field. And we want to estimate the position of an object located behind. So in this experiment, we used a second spatial light modulator in order to display our object, and we were looking as a parameter as the phase delay that has been applied by this small phase object onto the wave that has interacted with it. Then from the field measure from the camera, so we measure the data X with some noise. We apply the maximum likelihood estimator, and we end up with some values of theta that have been estimated. We've reproduced this experiment in two cases, for the plane wave case and the optimized case. And to make it clear that it worked, we made the true value of the parameter shift between two different values of the parameter periodically in time. And when we send a plane wave here and we apply the whole process, we end up with a signal that does not look at all by the value of the parameter that we like. And now, if we apply the optimized waves that maximize the Fisher information with respect to theta, we see that by using the maximum likelihood estimator at the end, we are able to properly recover the phase step that has been applied on your phase object. And as you see again, it's not a matter of a few percent. Here, it's the precision has been increased by 1 order of magnitude. So the standard deviation of this signal is 1 order of magnitude lower than this one. The last question that we can think about is, okay, I have built a way to be very sensitive to my object in reflection, but what's happening at the position of the target? Because a lot of people were saying, you're just focusing onto the target. Well, it's not the case. If you want to focus onto the target, this is the field that you obtain. But here, this is the field that you obtain. So, of course, it looks a bit like focusing because you have a lot of energy at this position, but it's not focusing. It's something different. And we were trying to understand in which way it was different. And in fact, we can understand it when we think about the relation between information and applied perturbation. So here, what I've talked about is the Fisher information in the reflected field, which is described by this formula, which has been introducing before, and which is driven by this operator, which is Hermitian and which is called f theta. And we want to connect it to the perturbation applied to by the field to the target, which is described by another Hermitian operator, which is called q theta here, and which is expressed in this way. When I say perturbation, is how strong the field is going to push your particle due to radiation forces. And when you see these two expressions, there's something very interesting which happens, is if you assume that the scattering matrix is unitary, then you see that this operator becomes the square of this operator, which essentially tells you that if you want to have a lot of information about your particle, you need to perturb it a lot. Then you can ask, but what is this condition? This condition of being unitary is that your system must have no absorption, so it must respect energy conservation. And also in experiment, which is problematic, is that you need to measure all the field that is escaping your system. So not only the field in reflection, but everywhere. So it's quite a strong condition, which is needed to have this perfect analogy. But even though it's a nice theoretical relation that have not been demonstrated experimentally so far. So with that, I'm just going to summarize my talk. So first, I talked to you about phase aberration in astronomy, in the regime where the index of refraction was weakly perturbed. And then I talked about multiple scattering, so in the regime of the index of refraction was strongly perturbed. And if you can play with incident field, if you can shape it spatially, then you can focus light, or you can also maximize the information about observables that are of interest to you inside your medium. And with that, I'd like to thank you for your attention.
Thanks a lot. So we literally changed focus, so because we are talking about waveguides, integrated optics, so now we've been to 3D. So we have some time for a couple of questions.
how do you?
Yes. Yes.
Is it working? How do you experimentally focus, change the shape of your light? Like, is it with like optics or like?
How do I shape the input light?
Yeah, the wavefront.
Yeah. So the idea is to use either a spatial light modulator or digital micro mirror device. So these are devices. Maybe it was not clear from these pictures. Well, yeah, these two pictures. So let's say you have this device. So you have a small device that is maybe like 5 millimeter by 5 millimeters, which looks like a mirror, but which is composed of millions of pixels. You see that it's a magnified view of what's happening here. You have millions of pixels, and each pixel can be controlled independently. You control it with your computer. So you can say for each pixel, it's either in this position, or this position. So in this way, you can flip all the mirror, and with some optics in between this device and your sample, you can convert this modulation into a full amplitude and phase modulation. So then the detail of the optics in between is a bit complicated, but if you're interested, I can send you some good papers. But we have ways that is called lithography to do it, which is some kind of Fourier filtering combined with this dispositif.
Benoît.
So thank you very much for your nice talk. So this slide is a good one. So you polarize the input light. What about the analysis? Did you perform a polarization analysis?
Yeah, so in most experiments, what we do is that we send a linearly polarized wave because it's easier. And then when it propagates through the complex material, it depolarizes typically. So you put a polarizer at the output in order to recover a single polarization to have a fully developed speckled.
Is there an interest to analyze, so to rotate the polarization at the output?
Yeah, the interest is that if you want to characterize fully your system, you need to measure both polarization. So this was in the scattering matrix construction here. So typically in the community, what we do is we measure only the EX component. But if you have an analyzer at the output that you want to rotate, you can also measure EY. The thing why we don't do it so often is that because these degrees of freedom are not coherent, so you cannot play coherently with them. So you can play coherently with all these ones, but not these ones because they are cross-polarized. So the expected gain of intensity is not that much. It's just a factor of 2.
So thank you for this very nice presentation. Well, I was thinking if it's possible to push forward this approach to do some, for instance, imaging through a scattering media. You have a scattering media, you have an image, and then you want to know this image to using this scattering matrix. Is it something possible, or it's?
Yeah, so it's a big goal in the field because all people want to do imaging. So there are many approaches that have been developed, but none of them have been proven to be optimal. So what I've shown you here is a way to describe it in the optimal way. So you can show mathematically that you maximize the Fisher information or you maximize intensity. You have no approach that tells you for sure that you will maximize the image quality, for instance. But my ANR project is to apply this idea of Fisher information to do imaging. And so you can have connections. If you can describe your image by some parameters, then you can apply the same mathematical formalism of Fisher information in order to recover the parameters that describe your image. Here, the idea of Fisher information...
Modulation transfer function, for instance, like we use for classical imaging, you cannot have the equivalence of this FTM.
Well, what you can do in the idea of transfer function, it's a bit about the idea of measuring the scattering matrix and inverting it, because it's essentially that. It's just you characterize your medium, and then you say, now since I know the scattering matrix, I know the transfer function. And if you want to optimize for the transfer function, you would need to optimize for the scattering matrix itself. Also, the problem of imaging is that typically it's not very well defined what you want to optimize. If you want to be very precise at details. So my approach is mostly to say that we define properly which parameter you are interested at the beginning, let's say the position of a tumor or the size or the position of the defect, and you're not interested at all in what's happening else in the image, and you optimize only for what you're interested.
Yeah, I have a related questions about the value of n. If I want to image 1 square centimeter, how much is this n values there, and how big is the payload in terms of computer hardware to manage these big matrices?
So n can be is too huge to be handled, to be clear. If you want to control all of the optical modes, in practice, in terms of we are limited by the hardware, and if you do like 10,000 modes, it's already quite nice. Just for matrix inversion, for instance, 10,000 by 10,000 is already quite big. But it's not a problem too much for the conceptual approach. It will still work, but it would work better if you can handle all of the modes. It's more than you have more information that you don't use, but still the technique that you build will allow you to benefit from the several modes together, so it will be better to do that than nothing. But you would still have a lot to gain if you would be able to handle the millions of modes that exist. But this, for sure, right now, we are not there yet.
Does it limit the field of view that you can, where you can use this technique to be efficient, or does it mean that the field of view is limited by n about 10,000?
So the field of either the field of view or the resolution of your image is limited. You have a trade-off because of the number of modes.
Any question from students? No? No? Okay, Antoine?
So sorry for handing the mic. Is it possible to have a kind of singular matrix expansion in order to select the modes that are the more interesting for your purpose, and only to focus on the mode with the highest weight, I would say, on the
like with the SVD, you mean?
Like a singular value expansion of your matrix.
Yeah. In fact, this is the way that we do focusing when you know the scattering matrix is performing singular value of decomposition of the scattering matrix, which is something that I didn't talk about. But when you invert the scattering matrix, in fact, you don't focus light. You try to make them all zero except of one at a position, which is not the same as maximizing the light at a position or not caring about what's happening elsewhere. So this is the difference of SVD-based approach, where you will maximize the energy at a position, on the scattering matrix inverse, where we'll try to build a pattern with zero everywhere on the one or point focus. So this is different, and in practice, the SVD approach works much better because it's less prone to noise, because you select the waves that are the strongest, so they are not prone to noise.
Yes, thank you. Because you made the analogy with the guide star, I would like to know this luminescence particle, if you have to move it close to where you want to work, or you spread out in the system different ones. And I want to know about polychromaticity. Is there an interest to change the wavelength of the fluorescence for the analysis?
Yeah, so about the guide star, it's true. If you want to do imaging with the guide star, you would need the guide star to move in order to be able to probe different locations. So that would be needed. I didn't explain it that you can use this technique for imaging, but for instance, if you are able to focus onto a guide star, then you can move a bit the focus in order to try to make an image by moving the focus. Because if you scan a point light, then you can recover an image. But this is limited by the isoplanetic patch that is defined by the medium. And if it goes outside the isoplanetic patch, then you need to move the guide star in order to probe different perturbation in your medium. About different wavelengths, yes, there have been several people that have been measuring this as a function of the wavelength. So you can you have even more degrees of freedom to play with, because you can also shape, for instance, the waves in time, not only in space. So we do it in space because it's very convenient. We have the tools to do it in space, and it's very very easy. In time, in optics, well, some people are doing it very nicely. For instance, at Lillier and so on. But it's more difficult than in acoustics, for instance. So first we do the demonstration in space, and then we go to time. But it's also interesting in this perspective to measure it as a function of omega. Yeah.
Any questions from the students? No. Okay.
Okay, so thanks a lot, Dorian.
Thank you.
You can run your presentation with that, and you have the laser pointer. Can we make a test of the sound? Or? Okay. So we close this morning session by a last talk coming back on quantum optics. So we have the pleasure to have here Villassini, who is a research scientist at the INRIA Center of located at University Grenoble Alpes. I think you are located in Minatec, I think. Exactly. And the title of the tutorial of Villassini is Entanglement, Bell Inequalities and More, an introduction to the power of quantum correlations. So please.
Perfect. I have the mic already. Okay. Thank you very much for the introduction and for the invitation to speak at this very nice event. So as mentioned, my talk will be more of an introduction to these very interesting concepts now studied in the field of quantum information theory, which is my area of expertise. And it'll be more of an introduction of these basic concepts while giving a bit of an overview into the kind of research directions that we look at, both on the more foundational side as well as on the applied side. Okay. And so let me start with an outline of my talk. So we'll start with a bit of a motivation for the field and give a brief recap of things maybe many of you have already seen before, but just to make sure we're on the same page, qubits and measurements. And then I will talk about what is entanglement, and as well as the concept of Bell inequalities. We'll soon see that it'll allow us to certify a form of stronger than classical correlations that we have with entanglement. We'll talk about some rather fundamental implications of Bell inequalities and their violation. And afterwards, we will move to talk about an entanglement-assisted protocol called teleportation and its applications for quantum networks. And finally, I will talk about some other quantum information processing applications and end with a summary and outlook. Okay. All right. So the field of quantum information theory sits at this very nice interface between physics and computer science and brings together rather important pillars from both these fields. On the one hand, there's quantum physics evolved in the last century, and where we have seen new concepts like superposition and entanglement and sort of quantization of classical concepts. On the other hand, in computer science, there's Shannon's information theory that gives a very rigorous framework to quantify, measure, and transmit information where the unit of information is measured in classical bits. And in recent decades, more like, this has led to the evolution of quantum information theory that combines sort of concepts and techniques from both these fields, and maybe more in its modern form. It's come up since the 1980s and 90s, even though many of these ideas have been around. And where the question is to ask what happens if we can encode and process information using the laws of physics, using the laws of quantum physics, and can we achieve anything that we could not do with the theory of classical information if we are now encoding information in quantum systems, right? And this has more recently led to the Physics Nobel Prize in 2022, as well as the Turing Prize. In fact, this should be 2025, actually, of last year. Okay, so just a quick recap. As you might already know, a qubit is a two-level quantum system, and it lives in a state space that we can write as which is a Hilbert space, characterized essentially by two complex numbers, so we would call it C2. And of course, there are many physical examples, like the polarization of a photon, horizontal, vertical, or energy levels, or spin states, and so on. And pure states of qubits, we will write them in this general form, where the 0 and 1 here is called the computational basis. This is the eigenstates of the Pauli Z operator. And as you can see, it's characterized by two complex coefficients that have to be normalized. And we also have other standard bases given by the Pauli X and the Y matrices. And the Pauli X1 is usually called the Hadamard basis. It's an equal superposition of the 0 and 1. Importantly, the global phase in a state doesn't matter physically. It cannot be physically measured. So these would be regarded as equivalent states. And a useful way to parameterize pure states is also instead using two angles. And so we can represent a generic pure state of a qubit in this way as well. And what's important is to be able to measure our quantum systems to extract some information. And generically, we are thinking of a quantum state going inside. So here I have described this by the state rho. This is, as we'll come back to this later, this describes what we will call density matrices. You can think of this as allowing for situations where perhaps I prepare one pure state with probability half and another pure state with probability half and try to mix them together. So for instance, flipping a coin and preparing different pure states. So that kind of scenario is more generally described by density matrices, which we will denote by rho. So in general, a measurement is going to take some input state and give us some classical outcome, as well as a post-measurement state of the system associated with getting that outcome. And the projective measurement is just given by a set of operators, this form, satisfying these orthogonality and completeness relations. And the quantum theory gives us the probabilities of obtaining these outcomes given our state rho using the Bond rule. Okay? And in the special case where rho is actually a pure state psi, it's represented this way, and the probabilities are simply given by the inner product between the projector and the state, right? And importantly, the state is updated when I see a measurement outcome A, then my new state is obtained just by applying the projectors to the previous state and renormalizing by the probability of the outcome. Okay? And of course, an example is a measurement in the computational basis on such a pure state. And clearly, the probabilities are given by the modulo square of these complex amplitudes. So there's inherently some randomness and probabilistic nature of quantum theory here, because given such a pure state, which is supposed to be a state of maximal information in the theory, we still don't know, and the theory doesn't determine which one of those two will occur when I measure it in the given basis. Okay, so extending that to the case of 2 qubits, so imagine I have 2 qubits now, A and B. Each of them live in a two-dimensional complex Hilbert space. So the joint state space of the two is given via the tensor product, and it's isomorphic to a 4-dimensional complex Hilbert space. And the computational basis of this, as you may know, is given, we can write it in this way, which is just telling us that the first qubit is in the state 0 and the second is in the state 0, and similarly for the others. Right? And so a generic pure state of two systems can be written, of 2 qubits can be written in this way, with this normalization condition, which is exactly the normalization of the state. And then, of course, an example is such a state, and in this case, this is a product state. It can be written as a product of a state of system A and a product of, together with the state of system B. But more generally, we will see that we can have more interesting correlated states. So indeed, that brings us to the definition of what a separable state is. So if we have a pure state of the 2 qubits A and B, we would say it's separable if it can be written in this product form as a state of system A, tensor state of system B. Okay? And if this is not the case for a pure state, then we would say that it is entangled. And as you may know, a very well-known example of an entangled state is this Bell state. And it's quite easy to prove that it's impossible to write this state as a product of any pure states of the two systems. And of course, a key consequence is that if the state psi AB is entangled, there's simply no way that we can assign pure states to each of the systems A and B individually, right? And so it raises a question of, can we still talk about the state of system A and the state of system B when we have an entangled state? And indeed, the answer is yes. But in that case, we would need to use density matrices and talk about reduced states. So one can take the state of AB and partially trace out the system B. Then one obtains the state of system A. And similarly, one can describe the state of system B by tracing out system A, okay? Which corresponds to sort of ignoring the system. But importantly, in the case of our Bell state, these two states, rho A and rho B, the reduced states will turn out to be completely mixed. So this would be equivalent to a coin flip that's completely random. So locally, if we look at each of those systems, they're going to look completely random. But even though if we look globally at the full state, there are these very strong correlations. And we will see how this plays a role in Bell inequalities. Okay, so just a little interlude to distinguish classical versus quantum forms of correlation, because you might ask, well, even in the classical world, we do see correlations. It's not that everything exists in product states, as we have seen before. So a very nice example is this story of Dr. Bertelsmann's socks, which goes back to this paper by John Bell. And this nice illustration is courtesy of Mathilde Baroni from Paris Sorbonne University. And so imagine that we know that Dr. Bertelsmann always wears mismatched socks. So if one sock is pink, the other will definitely not be pink, right? And now, even if we don't see both the socks and somehow distribute them to different corners of the universe, looking at one sock and seeing that it's pink definitely tells us that the other one is not pink, right? So this is not, clearly there's some correlation that can persist across distances, but there's no mystery here because somehow the colors were already predetermined, right? We already know beforehand that if one is pink, then the other is not pink. And we can write this whole scenario as a mixed state. You can think of this as flipping a coin and preparing, in one case, the first sock being pink and the other being not pink, and in the other case, the first sock being not pink and the other being pink, right? So you can write this as such a density matrix of two systems. And I gave the definition of entanglement for pure states before, but it extends also to mixed states. In that case, one would say that a mixed state is separable if you can write it as a mixture of product states. So in this case, this is actually a separable mixed state because it's just a mixture of product states. On the other hand, if we now had actually an entangled state of these two socks, this is fundamentally different from this scenario. And in the classical case, this scenario is really like a classical mixture, and we can explain it by the fact that the correlations that we see are predetermined. But we will see soon that in such a case, like this quantum superposition, there is not a meaningful way in which we could say that these colors were predetermined if we believe in certain other assumptions. And this naturally raises the question of how can we prove that these two objects are fundamentally different, and that in a way that we can actually maybe experimentally test this difference, right? And how do we show that quantum correlations arising in this entangled state are actually stronger than any correlations classically that we have in this separable state? And that's where Bell inequalities enter the picture, and they are a statistical test to distinguish classical correlations from genuinely quantum ones. And just a bit of a historical note, like you might know that this sort of entangled Bell state was the centerpiece of this historical Einstein-Podolsky-Rosen arguments, where they tried to use this to construct an argument to argue against the completeness of quantum theory, and to argue that perhaps quantum theory should be completed with some kind of hidden variables that allow you to determine what the states actually are, or what the outcomes would be. And in that historical context, Bell's theorem, in fact, which we'll see soon, showed that this program of completing quantum theory with local hidden variables is essentially impossible. So there's really some kind of fundamental indeterminism in quantum theory, at least under a few other reasonable assumptions. But I will take a bit more of a modern approach while presenting this. Okay. So I'm going to take the approach of this so-called CH-SH game, where we can think of these Bell inequalities as coming as a bound on the winning probability of some game that two agents, Alice and Bob, can play. So imagine Alice and Bob. Each of them have a device with some input and output, and these inputs and outputs are just classical bits for the moment, okay, as shown. And the game has two rules. The first rule is that they cannot communicate with each other during the game. However, they are allowed to share some common strategy in the past. So they're allowed to meet in the past and share some common information or strategy. Okay. And the second rule is that the inputs, x and y, the input bits, have to be randomly and independently chosen from this lambda. So they have to be freely chosen. Okay. And the winning condition of the game is that under these rules, Alice and Bob need to coordinate their actions so that their inputs and outputs satisfy this relation shown here as far as possible. So here, this denotes the modulo 2 addition of A and B, right? So if you look at this, what this essentially says is that whenever either one of x or y is 0, this product is 0, so A should be equal to B, right, in these three cases. But if x and y are both 1, A should be exactly opposite from B. So the probability of winning this game is 1/4 of the sum of these four terms. Okay? And now it's very easy to see that if we restrict Alice and Bob to live in a classical world and only use classical strategies, there's really a bound on the winning probability of this game. Okay? And let's see that. So if we impose these rules 1 and 2, then we cannot have Alice's output A cannot depend on Bob's input Y, and vice versa, because they have no communication during the game. And in a classical theory, one can define these variables. Essentially, this is telling us that given x and given lambda, Alice's outcome A is fully determined. So we have these variables, outcome of Alice when her input is 0, and outcome of Alice when her input is 1, which can also depend on lambda. And similarly for Bob. And then the winning conditions translate into 4 conditions on these variables. It's essentially saying that when x and y are both 0, then the corresponding a and b should sum to 0. Same for these two choices of x and y, but when x and y are both 1, these should sum to 1. And then it's easy to see that it's impossible to satisfy all 4. Because if you simply sum these 4 equations, you would see that on the left-hand side, each variable appears twice. So you see a0 appears twice, and similarly for all others. So when you sum modulo 2 any binary variable twice, this is always going to be 0. On the other side, you'll see that the sum is going to be 1, so you get a contradiction. So one can see that at most 3 of these conditions can be satisfied together. So clearly we can satisfy 1, 2, and 3 together. For instance, if I just pick a is equal to b is equal to 0 all the time, independently of x and y. So this gives the bound that the classical winning probability of this game is 75% at most. And this is, in fact, a Bell inequality. So it's precisely a bound on probabilities for any classical strategies that Alice and Bob could use while respecting the rules R1 and R2. And so in deriving this winning probability, we used a number of assumptions, right? The first assumption is often called locality, and this was telling us that Alice's outcome can depend on her input, but not on Bob's input, and similarly the other way around. And this was, if you think of these 2 parts of the experiment as happening in space-like separation, then this is really motivated by special relativity. The other assumption was that of realism, which was telling us that once I give the input and the information in lambda, then the outcome of Alice is perfectly fully determined in terms of these values, and similarly for Bob. And this is saying that we have well-defined values of all the outcomes in every run, even though actually in each run you only pick 1 value of x, 1 value of y, and only actually observe 2 out of these 4 variables, right? And finally, we also assumed free choice of x and y, that they are chosen independently of the lambda. And naturally, these assumptions hold in classical physics. In fact, we can't really choose to measure the position or momentum of a car, and can say that both have definite values regardless of whether we measure them. But we will see that quantum theory does allow to achieve a greater winning probability than 3/4, as we will just soon see. And Bell's theorem was precisely saying that no theory that satisfies local realism and free choice can explain the predictions of quantum theory, precisely because of such a violation that we will see. And here we can already take a moment to appreciate, I would say, the beauty of this theorem, because it is telling us that simply by observing a violation of such a Bell inequality, like if we have a theory that would violate this inequality that we derived under these assumptions, then we can be sure that at least one of those assumptions must fail in that theory. So you're able to test some fundamental principle based on what you can, the statistics of an experiment that you can perform with that theory. So if now Alice and Bob can share now an entangled state, A and B, and we'll say that in their devices, they are simply, now their inputs are choosing the choice of measurements they are going to do on the part A and B of this state, and the outcomes will be precisely the measurement outcomes. So let's define these bases as I've written here. Then the strategy is actually simple. So if Alice's input is x0, then she's going to measure the system A in the computational basis, as pictured here. If her input is 1, she's going to measure in the plus minus or Hadamard basis, which is 45 degrees rotated relative to this one. Bob, when his input is 0, is going to measure in this basis here, which is at an angle pi/8 with the computational basis. And similarly, when it's 1, it's going to measure in this minus pi/8 basis. And in this case, one can actually compute the probabilities using the bond rule. And I will not do the computation, but there's a nice symmetry. And one can see that the winning probability with this quantum strategy is actually close to 85%. and that's clearly violating the Bell inequality that we derived before. Right? So this tells us that quantum theory is not compatible with local realism or the idea of local hidden variables, of course, at least if we assume that the measurements are chosen freely. Right? And indeed, there has been several experiments performed that test Bell inequalities. And in those experiments, there's a slightly different form of the inequality that's used. That's called the CH-SH inequality. It's written in this form, more in terms of the expectation values rather than the probabilities. And here, the classical bound, the Bell inequality, is given by, as shown here. So this is analogous to the winning probability of 3/4. And the quantum strategy achieves this value, which is greater than 2. Okay? Right. And the way this is implemented, of course, there are many different implementations in different sort of physical setups using trapped ions or optics or so on. But this is a very basic sort of setup that one could have in a quantum optical realization, where one is now looking at polarization in entangled photons, right, that are emitted by some source. And one can, the choice of measurements are encoded in the orientation of the polarizers that are present here. And then one can sort of detect the different possible outcomes, collect the coincidence count, and estimate the value of S and check whether it actually violates a Bell inequality. An important thing here is that there are two main loopholes that arise in such Bell experiments. And the first one is called the locality loophole. And this is the question of, imagine that if Alice and Bob are not actually space-like separated, so you could then imagine that there is some signal that could propagate between Alice and Bob that, in fact, that would allow even a classical theory to fake a Bell violation. So in that case, we would not actually be able to certify that an observed Bell violation is really a non-classical effect, right? And similarly, if one has, for instance, very inefficient detectors, the detectors may not both detectors would click in every round of the experiment. So we might have to restrict to scenarios where both detectors gave a click or gave an outcome. In that case, one might end up with a biased sample where as well, depending on the detector efficiency, it can be possible to fake a Bell violation with classical strategies, right? So in the first case, the fix is to enforce that really these measurements happen in space-like separation, so that there's a very small time window between when these measurements happen compared to the distance between them. And the second case is to improve the efficiency of the detectors. That's one possible fix. And the loophole-free test tries to close both of these loopholes simultaneously. And a bit for the how these experiments evolved. So you can see the first Bell experiment was already performed in 1972 by Clauser and Friedman. Since then, there has been a lot of very sophisticated experiments. And finally, the experiments that managed to actually close both these loopholes, so the first loophole-free tests were only done in 2015, so you can see there's been like 3 decades of evolution on these experiments trying to close both these loopholes. Indeed, this was finally the subject of the Physics Nobel Prize in 2022 for these loophole-free Bell experiments, as well as several following experiments that led to applications of these in quantum teleportation, quantum cryptography, and so on, which we will we'll soon see those concepts. Okay. All right. And fun fact, maybe some of you knew already, Anton Zeilinger actually worked at ILL Grenoble during his PhD, which was something surprisingly I only found out after I moved to Grenoble. Okay. So a few foundational implications of Bell's theorem and in general of entanglement. The first is this no signaling principle. So even though quantum correlations are stronger than classical, they cannot be used for faster than light communication. And a way to see this is that if you look at the probabilities that we get, outcome of Alice will be independent of the measurement choice of Bob and vice versa, right? So Alice can locally not gain any information about what Bob is doing on his side and vice versa, right? And it's rather easy to prove this because independently of which measurement Bob performs, when we sum over his outcomes, this is a complete set of projectors, so it completely disappears, and we essentially get a state that only depends on Alice's measurement and her reduced state. So it's completely independent of the choice of y. So quantum theory satisfies the no signaling principle. And second important property is that of the no cloning theorem. So a question one asks here is whether there can exist a device that perfectly can copy an unknown quantum state. So more formally, the question would be, can there exist a unitary that can take a system Q in a state psi, which is unknown, and now give us 2 copies of psi? And the answer is no, that it's impossible to have such a device. And in fact, I won't go into the details of this, but this is to say that there's no universal cloning machine, but there can be, it's possible to clone some subsets of states. So for example, if I only have the computational basis states, 0 and 1, we can indeed have unitaries that perform this transformation on the states of the computational basis. But it would not work for all possible states psi. That's what the theorem tells us. And moreover, there's also possibility to do imperfect cloning. So if you don't want these copies to be perfect copies of the original one, and there have been bounds that have been derived. Again, I would not go into the details here. And in fact, these come up naturally in simulated emission processes and photonic systems, these sort of imperfect but optimal cloning bounds. I will skip through this quickly. I won't go into detail, but there's a very deep connection between cloning and signaling. In fact, if it was possible to perfectly clone quantum systems, it would be possible to signal faster than light. So somehow these 2 theorems are quite fundamentally related to each other. I will not go again into the details of this. Okay, so I'll highlight a bit some foundational research directions before going to the more applied side of things. So as we said with Bell's theorem, we know that these 3 assumptions cannot be simultaneously satisfied in light of the observations made in experiments that violate Bell inequalities. So it tells us that we must give up at least one of these assumptions, and this has rather deep consequences for our understanding of causality. So in particular, in the classical world, there's a framework called classical causal models, elaborated in this book by Judea Pearl and others, which is widely applicable in data sciences, so many data-driven fields. So for instance, if one wants to ask whether a drug actually causes recovery from a disease, or in predicting various economic patterns and so on, these models are widely used to look at observations and try to infer the cause and effect explanations behind them. And it was realized soon that these do assume a form of locality and realism because they're, after all, classical causal models. And one consequence of Bell's theorem that's elaborated in this work here by Wood and Speckens is that, in fact, these classical causal models fail to explain quantum correlations that can be obtained in these kind of Bell experiments. So it tells us that the best models we have for explaining causation, like connecting causation and correlation, really fail to be applicable to explain quantum correlations. So this has led to this whole research program that's called quantum causal models. And there's a lot of literature here. I've not had the chance to cite all of them, but some of these are mentioned here. And the aim here is to generalize these classical causal models by relaxing this realism assumption, to be able to give causal explanations without assuming this sort of determinism. And this leads to a genuinely quantum notion of causation, where one can still formalize notions of locality. And of course, this is a whole research program, and I won't get into it in too much detail here, as this is meant to be more of an introductory talk, but this is also mostly the area that I work on myself. But just to tell you briefly, here one can also connect these quantum causal models with the notion of space and time by embedding these kind of quantum protocols in space and time. And one can show that there is no faster than light influences in these causal modeling explanations of these quantum correlations once we have these more general notions of causal models. Okay. So even though one can surpass classical, but there's still a peaceful coexistence with relativistic notions. So as I said, it's a vast research area, but if you're interested, we will be organizing a conference called Causal Worlds later this year in Grenoble, which is really about looking at the interface between quantum, classical, and relativistic notions of causality, which have a natural interplay in the context of these kind of questions on entanglement and Bell inequalities, as well as trying to implement quantum networks in space and time. Okay. Right. Maybe I will skip through this part quickly and move on to the more applied side, but just to mention that quantum theory is not the only non-classical theory. In fact, one has shown that one can have beyond quantum theories that are still consistent with the no superluminal signaling principle, and which in fact will give you a probability of winning probability of 1 in the CHSH game. So as we saw, quantum theory only gave us about 85%, and turns out this is the maximum, the best we can do with quantum theory. But the literature one has explored beyond quantum theories that actually can achieve full winning probability. And I won't go into this, but this kind of play a role in trying to derive quantum theory from information theoretic principles and to really study what kind of information processing tasks quantum theory can do better than classical, or in which tasks can it be better than post-quantum theories, and so on. So to switch gears back a little bit, I would like to tell you about this quantum teleportation protocol, which is also another protocol that uses entanglement, and which is central to the construction of quantum networks. And so here the goal is that Alice wants to transmit an unknown quantum state of some qubit q to Bob. And of course, if she tries to send this directly, for instance, encoded in photons, these can be lost or disturbed in transit, right? And since the state is unknown, there's no way to sort of reconstruct it if you have no information about the state. So in teleportation, what one does is try to transmit this unknown state by using a pre-shared known Bell state between Alice and Bob, and then using classical communication, so whereby Alice could just give Bob a telephone call and tell him these 2 bits of classical information. Right? Okay, so the basic idea is the following. So Alice has this state of the system Q, and Alice and Bob also share this entangled state, right? And next, Alice performs a Bell measurement on her unknown qubit Q and her half of the Bell state. And a Bell measurement is essentially a measurement in the basis of 4 Bell states. I only showed you one of them, but you can convince yourself that you can kind of write down 4 different Bell states depending on the relative phase and the the correlations between the 2 systems, and this forms a complete basis of the 2 systems. After that, Alice sends classical communication telling the outcome of a Bell measurement, because it's one of 4 possibilities. It's a 4-dimensional space of 2 systems. This information on the classical outcome is sent to Bob. Bob then needs to use this classical information to apply a unitary locally on his system B. So this unitary really depends on this outcome A. And then one can show that in the end, he's left with the same state psi as the state that Alice tried to send, but on his system B. Okay? And just for a few key remarks, here there's really no transfer of matter or energy, but really of the information content of the initial qubit, right? Moreover, that this is consistent with the idea of no cloning. We are not copying the information that Alice had in Q, but rather that the state of Q is destroyed in the process, and we have recreated this unknown state psi on the system B. Moreover, one can check that it's consistent with no signaling. So before Alice actually sends the classical communication, Bob will have no information about this state. And moreover, this is somehow, there's no eavesdropping. So if you think of some third agent, Eve, who tries to intercept this classical communication and who tries to learn about this state psi that was there, she will not be able to do this if she only looks at the classical information, or if she only looks at Bob's system. Only when these 2 things are brought together can we reconstruct the state. Okay, and this can also be extended to teleporting 1/2 of an entangled state. So if this Q is entangled with some other system R, we can teleport Q, and the result is that in the end, this system R is entangled with the system B of Bob. And this is called entanglement swapping, and it's useful because we could start off with 2 entangled states separated by some distance R, each of them. But after doing this protocol, we now have entanglement between distance 2R, right? And this is a construction that's at the center of what's called quantum repeaters. Okay. Yes, so just to tell you briefly about these quantum repeaters. So in optical fibers, like the photon loss typically grows exponentially with the distance, right? So, and one can show that the average number of trials that one would typically need for generating a Bell pair or a Bell state across some distance L scales exponentially with this distance L, and where this L at is the attenuation distance associated with the fiber. And a solution for this is to use repeaters, which allow to somehow increase the distance while trying to minimize the loss in the signal. And here, I should say that classical repeaters that are used to scale up distances often rely on copying the signal and to amplify it, which we cannot do in the quantum case because of no cloning. And in the quantum case, quantum repeaters usually use entanglement swapping, which, as we've seen, is consistent with no cloning. Again, I won't go into a lot of detail here. This is a figure taken from this nice review article, which is on quantum repeaters and their applications for quantum internet. But here one can show, in fact, the important thing is how things start scaling once we add these kind of repeaters. So you can see that this protocol here is used to generate entangled states between distance L0. So you have many such pairs of entangled states. And now here we take one half of this state and one half of this state and perform a Bell measurement, right, to do the entanglement swapping. The result is that now we will have entanglement between these two at the further distance, and we can keep repeating it to kind of expand the distance between which one has entangled pairs by adding more and more of these Bell measurements, or these more of these repeaters. And generally, if you have capital N number of equally spaced repeaters, this number, the total number of trials needed to generate Bell pair across the distance, starts scaling in this way, where you now see that the exponent is divided by this number of repeaters n. And in particular, this PS is really the probability of success of this Bell measurement, giving the right outcome. And this is usually a constant that is independent of n. And one would get something that scales like this. So you can see that adding quantum repeaters, at least in theory, allows for a sort of exponential improvement in this total number, right? So this is at least in theory. Of course, there are a lot of still challenges to overcome on the experimental side of things. And this has applications for long-distance quantum communication and quantum internet and such. Okay, so I will briefly talk about quantum cryptography in one slide and then head towards the summary and conclusions. So another application of entanglement and Bell inequalities is in quantum cryptography, where the task is, say you have Alice and Bob who want to communicate secret messages with each other. And in particular, this is possible if Alice and Bob actually share a secret key, which is not known to anyone else or any other potential eavesdropper, right? And this is the task known as secure key distribution. Okay, so here I'll give a very sort of brief overview of how one could go about quantum key distribution using Bell inequality violation. I'm not going into the details. It's quite involved in actually proving the security and so on, but this is just to give a schematic of how Bell inequalities get used here. So here I have Alice and Bob, and they can share some entangled particles coming from some source. But importantly, now the source could be under the control of some eavesdropper, Eve, and they might not be able to trust this source. Okay? But they still want to use this somehow to generate some key, secret key, that the two of them share, and which they can be guaranteed that Eve does not know about. And they could try to use a Bell inequality violation for this. So if Alice and Bob actually observe a Bell inequality violation, which lead to strong correlations between their measurement outcomes, in fact, one can show that this really certifies that there is some secrecy in the key that they can generate from those outcomes. So of course, they would first have to violate Bell inequalities and then do some classical post-processing where they can communicate through some classical channel. And in fact, Eve could also be eavesdropping on this classical communication. But the idea is that using a Bell violation, one can certify that there's some genuine randomness in the outcomes that they obtained. And this randomness can somehow be amplified and made private so that they actually can extract a secret key, even though the classical channel and the initial source of entanglement could be under the control of Eve. This is quite a powerful property. And in fact, really the measure of Bell violation, which is the modulus of S minus 2, actually can be treated as somehow a security parameter to quantify how much security one has in this scenario. And in fact, one can see that if Eve really tries to measure this quantum state, like if Eve actually uses and measures the state before sending it to Alice and Bob, she will introduce some disturbance in it. And such, this disturbance can be detected by Alice and Bob. So in some sense, the protocol is also tamper-proof. And indeed, she also cannot silently copy this information and try to replicate the experiment herself because of no cloning. Just to comment that here, this example is a so-called device-independent quantum key distribution protocol. What this means is that we are only looking at the statistics that the devices produce, but not having to trust what is the state prepared by the source or having to trust exactly the measurements implemented by Alice. So that's sort of the powerful theoretical aspect here, that if I see a Bell inequality violation, it tells a lot of information without necessarily having to know exactly the state or the measurements that were used to derive the violation. But the original protocols that were developed initially by Bennett and Brassard and Eckert, they were so-called device-dependent protocols based on sharing particular states and measurements, and they had other advantages in security properties and so on. So the field really studies both these type of protocols. Okay, and just a comment that in classical cryptography, security usually comes from computational assumptions, or assuming the hardness of solving some mathematical problems, for instance, such as the hardness of prime factoring. In contrast, in quantum cryptography, the security is really certified by the laws of physics, at least in theory. So it's really qualitatively very different, right? And so in principle, as long as quantum theory is a valid theory, in theory, these protocols are secure. Of course, ensuring those security guarantees in experiments is one of the big challenges in order to overcome and to build these kind of protocols. So I'll skip through to the end. There are many other fields with quantum advantages and where the notion of quantum advantage is used in a very broad sense and can mean slightly different things depending on these fields, which I have not touched upon in this lecture. And it's quite a diverse and rich sort of community and where many of these different aspects are sort of explored within different communities of quantum information. Yes, then I will go to the summary of what we've seen, which was we looked at what entanglement was, its application for Bell inequalities, and we looked at both fundamental and applied aspects of these, and as well as looking into entanglement-assisted protocols like teleportations and how it forms the basis of quantum networks. In terms of outlook, there's really a lot of exciting research directions, and the beautiful aspect of this field that I find is that there's really a very beautiful synergy between asking fundamental questions about how quantum theory is different from classical, and on the other hand, actually being able to use that to perform some information processing tasks better with quantum theory than classical on the applied side. And I will, since I think I am running out of time, I will just show this outlook slide. And maybe just mention that even in this domain of quantum causality, there's a lot of further questions one can ask, such as what happens if we extend the notion of entanglement or superposition to things like causal order itself. So if you have a superposition of Alice acting before Bob and Bob acting before Alice. And these are sort of things we explore in our group, in the Quantum Info group in Grenoble, as well as sort of applications of these kind of new kinds of non-classical phenomena. And yeah, there are a number of these other topics. I'm happy to go into it more details if there are questions, but I think I will end there. Thank you very much. Leave it some.
So thank you, Vilasini. So maybe before we ask questions, I would say for those who will stay this afternoon, if you never saw an experimental implementation of this, you will have an opportunity to look at a device that produces entangled photon pairs. And maybe you will see that it's not so impressive nowadays because the setup, it can be built in 20 centimeters square. Whereas if you look at the pioneer experiments at the time of Alain Aspect and others, it used very complex lasers and full optical tables. But this afternoon you will see how we can experimentally measure the violation of this, in fact, CH-SH inequalities. But time is open for questions, so please, questions. Yes.
Hi, thank you for your presentation. You talked about the 3 assumptions that are used for the Belen equations. Could you, maybe, I guess it's also part of the conference you guys will have in Grenoble,
Yes.
but can you give us a sense of which of the 3 assumptions are in the community are thought to be this one we should bring down in a way? Is there like some classification? Okay, this one we feel is the strongest and most difficult for some reason to loosen, and maybe this one is better. Or can you comment on that?
Definitely. That's a very interesting question. So let me just go back to the slide with the 3 assumptions. I think we're almost there. Yes, I think it was even before the quantum strategy. Yes, here. So indeed. So one thing I should say is that indeed there have been approaches that explore the consequence of giving up either one of them. And indeed one can classify these different approaches. So for instance, if you want to keep, let's go one by one, right? So if you want to keep A2 and A3, so this would mean like keeping realism would mean that I want to kind of keep my classical intuitions about determinism and so on. But if you're willing to give up locality, this means that you're willing to allow some sort of superluminal influence in your theory, right? And there are models to do this. For example, there's the interpretation of Bohmian mechanics, which does this in a very clever way, in the sense that even though at the level of observable probabilities, you would still satisfy this no signaling principle I told you about. So Alice and Bob cannot actually use this to send faster than light signals. At the level of the theory, one adds, in addition to sort of the quantum prescription, you have something called a pilot wave that can sort of spread out outside the light cone and kind of guide your quantum particles in a way. So one can see Bohmian mechanics as in some sense violating the first assumption, but preserving the other 2. And now this, what I mentioned with these quantum causal models, is on the other hand trying to preserve locality and free choice. So all your causal influences stay inside the light cone and you keep your free choice, but you relax realism. So you don't require that your outcomes are really predetermined by some variable lambda and by your input. So you really allow for this randomness. And so then you're kind of generalizing your notion of causality by relaxing this A2 assumption. And this is quite, like at least in the conference I mentioned, this is quite a widely used perspective. And of course, within that, there are many different approaches. And finally, if you want to keep A1 and A2, but relax A3, this leads you towards approaches that are called superdeterminism. But there's like many, within that as well, many different approaches where one could kind of give up free choice in a sort of weak way, but not in a very strong way. And then people try to still recover the predictions of quantum theory. So the mathematics of these models start looking very different. But people have explored these 3, and indeed, that's quite interesting.
Okay, other questions? So maybe I have one. When you say that about you have to close, people have to close loopholes, one of them was about detections, you say. How do you close this loophole? Because in practice, detectors have finite yields and so on. So how do they close this loophole in practice?
Yes, no, that's a great question. So indeed, with this detection loophole, yes. So here, there's actually what people derived was some sort of bounds on the detector efficiency. So now you're really thinking of your Bell experiment with some inefficiency on the detectors. So which means that you allow for situations where it could be that the 2 detectors did not click. You sometimes have 1 click and 1 no click, or sometimes both no click. And then one has to describe how we account for those no-click outcomes. And in that case, one can really use the parameter of the detector efficiency, eta, to compute what would be the CHSH violation as a function of eta. And one can show that then like this winning probability or the Bell inequality bound is also derived relative to the eta, so that one can say that if my detector efficiency is lower than this threshold, then there exist classical strategies that can reproduce this Bell violation. But there's still a non-trivial threshold, which is not 100%, which above which you can be sure that this was still some kind of quantum violation. So this threshold initially was quite high for CHSH. It was 80-something%. But then there's a whole lot of research on exploring other types of Bell inequalities, which can have better thresholds. And in fact, there's one called the CH inequality or the Eberhard inequality, where the threshold goes down to 67%, and this was something that was then doable. So then that's also a wide research area to explore different types of Bell inequalities. So for instance, here we only restricted to the binary input, binary output case, but there's a whole rich landscape if we go beyond that, and also for different types of scenarios, and then these can have different behaviors with the efficiency.
Okay. So if I rephrase, if I have the practical detectors, the threshold is not at 2, is higher than 2, or this is it?
Yes, so you want to observe a Bell violation, but also be sure that the detector efficiency is above some threshold. So it has to be high enough, but doesn't have to be perfect.
So the less efficient are the detectors, the higher is the threshold to...
Yes,
okay.
Exactly.
Okay. Okay, other questions? Yep.
Yeah, also on this slide about the locality loophole, when you say switch things faster than light travel time, but the device that you use to switch things, they also share a common history. So, I mean, how do you make sure that they are random, right? They are not going to be random because they share the common history, so they can do the same stuff on both arms, right?
That's a good question. So indeed, like this locality loophole, like, so in a sense, there's also an additional loophole, let's say, in terms of the free choice, because we had, like with these three assumptions, we had to ensure some kind of locality, but also that these inputs X and Y are really chosen randomly. So one tries to really generate these X and Y with random number generators, and sometimes in more sophisticated experiments, in fact, one uses some kind of quantum random number generators. And of course, there is some level of trust there that there isn't some spooky mechanism that correlates your source together with these random number generators. But given that, then the locality loophole is closed by, for instance, here, already in the early experiments of ASPE, they were able to switch this, so they're able to use these random number generators locally, fast enough to generate the X and Y, and be able to switch those settings faster than the time taken for light to travel between Alice and Bob. And then this has, of course, improved in much more in the recent times. If that answers your question, I'm not sure.
Yeah. But I mean, if you have to use a random number generator based on quantum theory, is there kind of inconsistencies that can break the whole thing, or is
no? That's a great question. In fact, so that's a great question. So indeed, like you might say that, well, the point of Bell inequality is to certify randomness through quantum theory, but then you use quantum random number generators already, right? And indeed here, then it really goes down to the numbers. Like one has to really look at how much randomness am I consuming and how much am I generating. Indeed, there's the whole field of quantum random number generation and amplification, where one can show that there is a way to do this non-trivially, in the sense that you are consuming less randomness than you generate. Yeah. So indeed, it goes down to how much you want to trust. For instance, okay, these two loopholes are still barring somehow this free choice question, right? And I think that is somehow the loophole that's almost impossible to close, because there's almost no way to certify that there isn't something that correlates your source with the inputs you generate. But for this, people have also done this sort of cosmic Bell tests and other sort of scenarios. But for your question of randomness, indeed, one can try to quantify it and show that really the randomness going in is smaller than the randomness coming out, and you can repeat it many times to amplify the randomness you get out. Yeah.
Other questions? Maybe. Yeah, your one.
Yes, it's about the threshold in the game. So you mentioned that thanks to quantum mechanics, you go from 75 to 85%. But you mentioned that you can get to 1 by keeping signaling. So what are the physical ingredients in that case? What do they share actually more than quantum mechanics qubits to get to this unitary probability?
Yes, that's also a very interesting question. So let me go to the slide where I think it's a bit later. Here, yes, indeed. So in this figure, so one thing I should say is that if we are really restricted to quantum theory, it's really this 85% is the best one can do. But then people started asking that what does a theory need to have to allow for this unit winning probability? And in fact, in this early work by Popescu and Roelich, they came up with an object, like it's a theoretical object called the PR box, and which, if Alice and Bob share it, they can achieve this probability 1. And in the following work, this kind of situations are formalized within this so-called framework of generalized probabilistic theories. So this is a bit like a large landscape of theories where you say that I have some description of my state space and I have some description of my measurements and transformations that preserve the state space. And so it gives a sort of abstract framework to describe a class of theories where, of course, classical theory and quantum theory are specific examples. And within this, one can find some notion of generalized bits, which are a bit more general than qubits. And one can describe these PR boxes as being like correlated states of two generalized bits. And indeed, and that naturally leads to the kind of question you're saying of precisely like under what conditions do we get back quantum theory and how are these theories different from quantum? And there's this whole research program to really try to understand it from physical principles, because it's known that these theories, of course, satisfy the no signaling principle, but clearly that principle is not enough to single out quantum theory. So an additional principle that was looked at is called sort of information causality, which is to ask not just whether Bob can signal to Alice, but to really quantify how much information can Bob signal to Alice. So if we allowed them to exchange only one quantum bit, then how many classical bits can they communicate in that? And for the case of qubits, actually, if you send only one qubit, then you cannot communicate more than one classical bit. But for these generalized bits, they actually allow you some very non-trivial and huge communication complexity. So in the spirit of complexity theory, one could say that if you believe that the world doesn't give you a free lunch to have this kind of communication complexity, you might not believe those theories are physical. But that's a bit the research direction. Yeah.
Does anyone has any hints on how to have an experimental proof of this an object that can go beyond this quantum? Because we have the entangled state for quantum for the quantum limits, but to go beyond, do you have any idea of how should be look like?
Yes, so I think the general belief is that these theories are not very physical, that we don't expect to be able to do them. But in the context of like quantum gravity and these more exotic proposals, there are some models which propose that, okay, in these very exotic regimes that cannot yet be tested, maybe we might see something like PR boxes. But these are very speculative. So in that sense, I think it's not believed that we might be able to find something from those theories that's beyond quantum, I think. But it's more studied on the theoretical side to shed light on the structure of quantum theory, I would say. But indeed, that would be really cool if someone can, in the far future, find a way. Yes. Yeah.
Maybe I have one last question. We saw yesterday that, for instance, at Quandela and else, you can prepare multi-parted photon right. That are entangles. If I want to characterize this entanglement with more than 2 photons, or in triplets pair, for instance. Is there a similar way than measuring Bell parameters, and how it can scale with number of photons, for instance?
Yes, also a very interesting question. So there are like sort of Bell inequalities. Also, one can formulate for multipartite entanglement and other scenarios, even network scenarios where maybe you have Alice, Bob, Charlie, and then they have 2 independent sources of entanglement and these kind of more complex structures. So there's sort of the field of Bell non-locality and network non-locality. There are a lot of techniques to try to define Bell inequalities and similar techniques in that case. But the problem does get quite complicated, because one wants to ideally, if you see like here, the Bell inequality is some facet of, like, you have this is like the space of correlations, like each point in the space is one P of AB given XY that you can generate from the experiment. And so this is the set of all the classical correlations, and a Bell inequality is like a facet. This is usually a convex set, and the Bell inequality is a facet. So if I violate it, I know definitely that I'm not inside this green thing. And these sets start looking really complicated in these higher dimensions. But in certain cases, this has been done well and also been tested in experiments, some of them including the Nobel or Zeilinger and others. I think in the tripartite case, it's with qubits, tripartite qubits or so on, it's quite well understood as well. I think
but it's more and more difficult if you increase the number.
Yes, already in theory, it gets very difficult to characterize, like, for instance, the problem of characterizing all the Bell inequalities. So in this case, of course, this is one Bell inequality, but by sort of taking symmetrically, like rearranging the terms, you can get, like, this is also a Bell inequality, this one, like each facet is a Bell inequality. So really characterizing all the Bell inequalities in these bigger cases starts becoming a really computationally difficult problem, like NP-hard, this sort of thing. But indeed, in special cases, there are techniques, and in many cases, it's enough to know just one inequality and you know a quantum violation, like, then this already allows you to certify, and so there's still a lot of hope for progress, even though it's known that the full problem is very hard.
Okay.
Yeah.
Okay, I think unless you have a last question, we have to close the session, and we have to thank Vilasini again for her presentation. Back the mic to Patricia to close the morning session.
Thank you, David. So thank you, everybody who stayed to follow these lectures until the end. Think about that. You will find all the recording will be available online. Okay, and since you assisted the lectures, we will ask the speakers if we could get slides, and if you want them, you can just ask. Okay, if you want the slides, and moreover the recording that you will see online. Okay, please, the ones who stay for the experience this afternoon, stay in the room, and the others, you are free to leave. Thank you very much. Okay, we can. Yes, and thank all people who are online. We don't see them, and thank a lot.
No, it's okay. Right, just for the feedback, so after you've filled in the feedback form, you can again have the certificate for this day. And also, so the certificate will label if you are here for the tutorials or for the whole day with the training and so on. So you can apply for that specific certificate that you need after the feedback form. So make sure to have the QR code for that. Thank you.
Just to be clear, could those who will stay there for training can raise their hand just to check how many you are? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so you stay there, or then we will have a lunch first to get all together, and then after we'll start the training at 2 p.m. after the lunch.